dancing in the party for show. Slip my girl a 44 when she crept in the back door. Chickens looking at me strange, but you know I don't care. Step on Eagle Double G. Snoop Dogg. Snoop Dogg. Da 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 da. You know I'm mobbing with the Eagle Double G. Snoop Dogg. Snoop Dogg. Da 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 da. You know I'm mobbing with the D.O.E. Yeah, yeah, yeah. You know the West Coast is back for all you suckers, suckers. So put something in there. Smoke weed every day. It's the one and only D.R.E. Dr. Dre love bust. You know I'm mobbing with the D.O.G. Straight off them killer streets of CPT. King of the beach, you ride to him in your fleet. Wood, the Ville rolling on dubs. How you feel? Whoop-de-whoop. What? Dre and Snoop hitting corners in the lag. With Doc in the back, sipping on Jack. Clipping all the amps, dipping through hood. Compton, Long Beach, Inglewood. South Central out to the west side. It's California love, it's California bug. Got your boy a gang of pub. I'm on one, I might bell up in the Century Club. With my jeans on, and my team strong. Get my drink on, and my smoke on. Then go home with something to poke on. Locust song for the 200. Coming real, it's the next episode.
Man go crazy. Legendary.
Perfect.
What is up, party people? All right, so this is what we're gonna do. I'm gonna go live, or I'm going live for a pretty specific reason. It has a lot to do with what happened on Jose's panel and the conversation of the EMPs. So let me go ahead and do something real quick. Let's see. Okay, so this is what happened. My bad. So this is what happened. I went on Jose's panel. They were talking about EMPs, and get this. There's a possibility, this off-going possibility, maybe, that maybe I don't have a full understanding of it, and I just wanted an explanation. What ends up happening is I came in the panel, on Jose's panel, and said to George, who was explaining it, that I didn't think that a car was a good example of something that would block the electric part of the EMP, because basically the windows wouldn't block that pulse either. The basis of a Faraday cage, my understanding of it is that it is an enclosed box, basically, somewhat the same, pretty much, as a microwave. And what would end up happening is it would deflect the pulse. Now, hang on. One of the things that I didn't understand about the Faraday cage is that a Faraday cage does not just itself block the electromagnetic pulse altogether. What it does is it blocks the electric pulse, is what I now understand from it. And you would have to add a shield, which is what blocks the magnetic pulse. That is a true, I guess, a true EMP Faraday cage. I didn't understand that, so I was trying to clarify it. I still, to this second, think that using a car as a example is bad, because it again, in any situation, I don't care if it's just the Faraday cage or we're talking a shield, a glass window is not going to block a pulse. So a car is not a good example of any kind of Faraday cage at all. I don't care. That's just what it is. What happened on Jose's panel had nothing to do with me trying to tell George he was wrong. It was me trying to say that I don't think a car is a good example because a car is not an enclosed cage. It's not something that you would use. In a car, if you're sitting in a car and someone set off the EMP, whether it's the electromagnetic pulse or the magnetic pulse, electric or the magnetic pulse that affects your electronic devices, it's going to make it through the windows. Not, so car isn't a good example altogether. I don't care. But down to the understanding of the Faraday cage and the shield, I didn't know that, and I wanted to hear it. What happened was when I then started to ask George to explain it better for me, George decided, or not George, I apologize. George actually didn't do anything wrong in the situation at all. Dress and a few others decide to all jump on the bandwagon of let's all say what we have to say at the same time. One of the reasons I don't run my panels to allow that is because it's fucking ridiculous. It's a fucking joke. It's an embarrassment to them. All you motherfuckers that think you're all geniuses and got something to fucking say, rumpus. It means jack shit all if anybody doesn't understand what the fuck you're saying or the topic. All I was doing was asking a fucking question, and you guys wanted to jump at me like I was a flat earther. Go blow yourselves. That's all I gotta say. And that goes to everyone. Druss is a good friend. I like Druss. But at the same time, fuck yourself. If I'm having a conversation with George and I made sure I addressed my question to George, shut the fuck up and let me finish my conversation with George. I'm not a fucking flat earther, dumbasses. I wasn't denying how an EMP works or what it fucking does. I didn't understand it. George was explaining something. He had said something that I didn't agree with. I threw my 2 cents in there. As soon as he said I was wrong, I asked him to explain it to me. I didn't say, George, you're fucking wrong. Shut up. I know this because me and George had a conversation on Jose's server. He DM'd me the explanation. And George, if you're out there still, I appreciate the fuck out of it. Thank you for explaining it to me. I've had conversations with George. Here's the fucking problem. Rumpus. Whether you're smart or not. And again, I think you're a smart person. The problem is you think you're smart should be understood by all. Your understanding of a situation should be understood by all. I've said this to you multiple times. Your explanations are shit. Your knowledge is fine. You can have the most knowledge of everyone here. But if you can't explain a simple thing to somebody like myself, then your explanation is wrong. Because I'm trying to understand it. It's not like I'm here sitting here denying what anyone's saying like that. It's literally the fact that your explanations suck ass. That's all it is to it. You say stupid shit like the horizon's a physical place. It's not physical, rumpus. We can argue that anytime you want. You can mishmash what the fuck you say, but the real idea of it is this. Ready? Rumpus, saying that the horizon was a physical place is you're wrong. Just fucking wrong. Went through extensive... I played your stupid clip of you saying it. I went through many streams showing how you were completely fucking wrong for explaining it the way you do. But here's the go. Here's how it goes. Your explanation was wrong. I cleared it up. And so if I have the opportunity to do that anytime I fucking want, I'm going to fucking do it. But the reality it is this. I didn't mean to do that. It is worth my time to do this. Goodbye. And the realization is this. Jump on. You can act as if you have the most knowledge of everyone, but if you can't explain it, again, like I said, it's shit. And I will, and here's the best part. I'm not trying to expose you, but I'll expose the shit out of your explanation and its wrong faults, like super looming rumpus. And it may have been okay, but listening to you jump on flat earthers for changing things like Travis did is ridiculous. You're just making up your own shit, and it's not an actual scientific term, so therefore searching it makes it seem pointless. Your explanation for the horizon was bullshit, pointless. Your refraction presentation was BS because, let's face it, if no one understands what the fuck they're looking at, your explanation is going in one ear and out the other. You're an asshole, so no one listens to you anyway. Again, I'll say this one last time. Rumpus, here's how it works. Everyone, both sides, talk shit for a reason. Maybe you need to think about that. There you go. Yeah, George. I just wanted to get through that because I heard Rumpus was talking shit. I haven't even heard it yet. Jose shared it. I'm gonna play it because I haven't heard it at all, and I'd like to hear what Rumpus's genius of words had to say about what I said. So let's go ahead and play that real quick, and then I'm gonna start sending out those links to. Oh yeah, so I'm gonna use the old Hangouts. Why? I don't know. I just decided to use the old Hangouts. But while I set that up and send some invites out, let's hear what the Rumpus had to say.
There was an idiot earlier who said, what's the link between gravity, E is equal to mc squared, and the Faraday cage? The answer is none. There's not supposed to be a link. Why you think there should be is absolutely ridiculous. No one's explained gravity to him. Well, it's about mass attracting mass. That has been explained to you. You're an idiot. And there are some other experiments better than the Cavendish that I think people were showing in here, and I've looked at before, where they have multiple balls, where they've amplified, they've done a new super version of the Cavendish, where they've got a whole ring of balls suspended, and they've magnified the effect of gravity, and that gives really solid results. And I've got questions basically saying my equipment doesn't work, therefore I can't detect gravity, therefore gravity is not true. He doesn't know the sensitivity of his equipment. He needs to establish that you can generate very small forces by having very small electrical charges. He's absolutely no idea how sensitive is equipment. So he's in no, you have to establish the sensitivity of equipment before you can say that this force of a particular value is or is not there. And also he's right. The one thing he did get correct is that weighing video. That is correct. The one he's referring to about the 1960s, about a little tetrahedron being dangled next to a lead ball, that is indeed bollocks. George and I did the maths on that, and it absolutely cannot be true. It's a factor of about 1,000 incorrect. So even if they had 3 more digits, you still wouldn't be able to do it. And so that's why you have to use the Cavendish. The Cavendish experiment is incredibly sensitive, and it's really the only practical way of doing it. If it was possible to do it with a little weighing machine, they would do that instead. And finally, how Just managed to hold his temper being faced with Sean, and how George managed to hold the temper being faced with Sean G, interrupting him systematically after 3 or 4 words when they were trying to get an important point out about the electromagnetic and the fact there's 2 components. And Sean just would not let George finish the sentence or just say something. You've got to stop that. I mean, that was just a disruptive behavior. And Sean is just an ignorant twat. He used to be a flat earther, and he should go back to being one, so we don't have to put up with his idiocy in here, and he can become a nice flat earther advocate, because that's where his intellect deserves to be. Thank you.
Yeah. And guess who was right on that one? Jose. Let's get one thing straight, Rumpus. And I'm going to repeat myself because I know you're out there, Rumpus, because you're a bitch and you don't have the balls to actually, speak up for yourself to me. I was talking to George, and if you go back in that recording, what will end up happening, Rumpus, is you'll realize that I'm having a conversation with George, and 4 people jump on it like it was like there are snakes on a mouse. So kiss my ass on that one, Rumpus. You have no idea what the fuck you're talking about. You constantly interrupt everyone with your bullshit rants. And again, let's make one thing straight. As smart as you think you are, no one gives a fuck what you got to say. We all laugh at you, make fun of you, and no one actually gives you respect. There's a reason for that, Rumpus, because you're a fucking asshole. And now you're just upset because someone calls you on your misunderstanding of terms, I guess. You're deciding to make shit up, I guess. I don't know. But the realization is this isn't Rumpus world, and you can't just make shit up, and this is Rumpus world. You can't just decide how things are going to go and be said. You're talking to people who don't understand science, and you talk to them like you're going to change everything. And the reality is no one listens to you. You get one or two rants in you, and people talk about it for a day or two. But all in all, Rumpus, you're just an asshole, and everyone knows it. Just realize that every time you get on a panel, and you start one of your bullshit rants, everyone is just waiting for your Rumpus catchphrases to laugh at you for saying. When you make it a presentation of something, guess what? Everyone tunes out, and everyone starts their own shit in the fucking chat. You're done, everyone then jumps back to the panel what the panel is saying. Why? Because no one gives a fuck what you got to say, Rumpus. You make presentations like you're talking to yourself, you conceited, narcissistic fucking idiot. So if the problem is that someone actually calls you on your stupid shit is the problem, that's a self problem that you got, motherfucker, not mine. All your disrespectful comments you got to me, come on my panel and fucking say them. Stop saying them on other people's shit when I'm not there. Otherwise, you're just a bitch. And everyone listening, and everyone that's going to hear about this is going to go, yep, Rumpus is a fucking bitch. Every single person that I've explained what happened today to goes, oh, okay. Why? Because of that, I explained it very clearly, even on Jose's panel, that I didn't fucking know. Didn't understand it. And that's something you need to understand. Being able to drop that fucking ego and realize that when you're wrong or you don't understand something, you can ask questions and want to hear it. All that hoopla that happened with Druss and all that shit had nothing to do with me trying to argue or not hear something. It was all me trying to listen to the one fucking person that was answering the question that I asked the question to. George. George was talking. Then Druss jumped in. And then whoever else jumped in. I cut those people off. Why? Because I didn't ask them the question. I asked one person. Why? Because when you have 5 people trying to tell you one answer, guess what fucking happens? You get 6 different answers. I wanted the answer to the person that I had referenced the example being wrong to. And again, I'll repeat this. Someone say I'm wrong about a car not being a very good Faraday cage because of windows, which is why I don't think it's a good explanation. And my whole point of how you explain shit to people needs to be simplified and better. If you don't want to listen to someone that's stupid and doesn't understand shit and is trying to tell you how to help understand some shit, fuck you then. That's your problem, not mine. I'm the one fucking person you need to be listening to when I say, hey, simplify it. Hey, I have a question. Because my questions are the questions that someone who really gives a fuck is. Meanwhile, you'll do these presentations and talk to flat earthers who don't fucking even realize how science even works, period, and explain it to them like they should know everything already, and they're trying to debunk it or some shit. No one's debunking anything, so why are you giving presentations like they are? Why do you spend all your day making these long, extravagant presentations for someone to say, nuh-uh, and then so you can call them a fucking idiot? That's why you look like the fucking idiot, Rumpus. That's why you're the fucking utter moron. So keep on with saying shit in my messages. Keep on saying shit when I'm not on a panel, when I leave the panel and I'm not there. Because everyone's always going to remember that you're a fucking pussy for it. You have no fucking balls. And your narcissistic ego is all that fault. So keep my fucking name out your mouth. Unless you want to be a fucking man about it and say it with me able to respond. Come on my panel and let's talk it out, Rumpus. Otherwise, shut the fuck up. That's all there is fucking to it. Now that I'm done with that, if you'd like to join the panel, here you go. George, if you want to jump on the panel and have a talk about it, I will have everyone, make sure everyone mutes and let you go. But I am going to open the panel for everyone to jump on if they'd like. Again, like I said, I have nothing more to say about Rumpus. He's a pussy. Doesn't have balls to say it to someone's face. It basically likes to be that utter guy, and everyone just laughs at him, and it's funny as shit. That's how real as it gets. you can make 1,000 presentations and no one's going to give a fuck or remember them. All they're going to remember is how piece of shit he is. What's up, George? How you doing, sir? And then before you start, I wanted to, yep, yeah, George. Before you start, though, I do want to say to you, I apologize. I wasn't denying anything you were saying. I was trying to understand what you were saying. So don't think any of that had to do. Okay. Mm-hmm.
You're considering and what the situation is. Different types of enclosures can be an effective Faraday cage in certain situations and a very poor one in others. And you just need to understand a little more about electromagnetic wave propagation and the nuances that go along with it.
Okay, so when I said a car isn't a good example, in a situation it's not. But the way you were explaining it, it was a good situation. So, like you were saying, it's pending on the context of it, right?
Yeah. Hang on a second. I got to let Con out. He's scratching at the door, and then we can get into it.
Yeah, no worries. Yeah, sorry about the sound, guys. Yeah, George was just kind of going over what we were saying. He said that the explanation of the car, we were both right, and then he started going into the context of what he was trying to say rather than, the bold statement that was made. But yeah. And if you have questions in the chat, make sure to tag me and I'll be able to get them out there too, if you're not on the panel. Yeah,
I'm with you now.
All right, what's up?
Okay, now this term Faraday cage, it originates out of Maxwell's equations, and Faraday was the first one before Maxwell actually presented his thesis and his publication on the equations. Faraday had discovered this effect of that an enclosed metal container will effectively block out an electric field, and all the charge that you put on a conductor resides on the outside surface. Now, this whole idea of Faraday cage comes about by looking at one of the four equations of Maxwell called Gauss's law, which basically tells you that all the flux that passes through a closed surface is identically equal to the amount of charge inside. And the standard thing that you do is that if you have no charge enclosed, so that this integral of E dot ds, that is the integral of electric flux over the surface, is equal to the charge inside. Well, if the charge inside is 0 and your enclosure, say, has spherical symmetry, you make it a sphere, then because of the symmetry of the geometry, it's easy to conclude that the electric field also is 0 inside. There can be no electric field inside an enclosed good conductor or enclosed metal container that's made of a good conductor. And it doesn't matter the shape, whether it be spherical, a cubic box, a pyramid structure, or whatever. The electric field inside an enclosed metal shield has to be 0. It's just a consequence of the boundary conditions in Max and Gauss's law. Now, the situation, what that means is, say, if you have this enclosed container, metal box, and you come along with a bunch of charge and you dump it on the box, say, like charge up a balloon, rub a balloon on your hair, get it charged up, and then touch the balloon to the box, all of the charge immediately migrates to the outside. nothing on the outside surface. No charge will ever be found on the inside surface. And the speed with which this does, the charge migrates is extremely fast. It's called the relaxation time. And for electrons, it's on the order of less than picoseconds, less than a billionth. Pardon?
That's kind of like in a way like when you a taser, when you hit somebody, the point of impact to the zero, back to zero, is what you're talking about. That relaxation or the.
Well, what the relaxation time is that, say, if you could somehow get to the inside surface of a metal container and you dump some charge on it, that charge will immediately go through the metal out to the outside surface, and nothing will be on the inside surface. There won't be any charge on the inside surface.
Okay.
And the time that it takes to migrate from the inside surface to the outside surface is on the order of a millionth of a second.
Okay, I get it now.
Picoseconds. It's very, very fast.
So it's the change in the time. It's basically like the change in the median of it.
The charge has to redistribute itself. If you put an accumulated charge on the inside surface of a metal container, say, like a gallon oil container, a gas container, if you put charge on the inside surface, it's immediately going to redistribute itself and go to the outside surface and distribute itself in such a way as to create what's called an equal potential surface. And if that surface was a sphere, the charge would uniformly distribute itself over the surface of a sphere.
Like a train, when you connect a train track, and then you have like the switch tracks. It immediately will connect the circuit, basically.
Well, I'm not sure what you're saying there.
It's like you're saying the transfer between.
Well, there's no circuit. What the charge will do is Maxwell's equations, Gauss's law demands that there cannot be any charge on the inside surface. So if you put charge in some manner, manage to put charge on the inside surface of a metal container, that charge will immediately migrate to the outside surface and leave the inside surface.
Okay, I'm starting to see it. I get it now. Okay.
It's moving.
Yeah, I get it now.
The charge will move. It will migrate from the inside to the outside surface. And the time that it takes to do that is called the relaxation time.
Yeah, okay. I get it now.
Very, very fast. Now, it turns out that in these static conditions, for the purist, you have to have what the purest definition of a Faraday cage is an enclosed metal container that has no holes. Okay, it's completely uniform, homogeneous material that has no holes in it. Well, you can relax that and still end up with a very effective Faraday cage. It doesn't matter if the container has holes in it, like a car where you have windows and that if I put charge on the inside surface, it will go to the outside surface, even though that there are holes in the structure. Now, that makes it very effective for, say, a lightning strike. I'm getting kind of dry.
No worries. No worries.
Lightning strike is dumping a lot of charge onto the outside surface of your car or a container, and that charge will stay on the outside and bleed off into the ground or into the earth if it has a path to do so. If it doesn't have a path, like you're sitting, this whole structure is essentially insulated up off the ground through rubber tires.
Mm-hmm.
And any charge that gets dumped on there will remain on the outside shell of the car unless it's so much that it breaks down the air, and you'll have an electrical discharge from the car, like you walking up from a dry rug and touch a doorknob or a faucet or something. You draw this spark, and so the charge gets bled off. If there's a lot of charge, that will happen. I mean, you'll end up with sparks from the car to the ground. But if that doesn't happen, that shell could be charged up to as much as 50,000 volts. And then if you open up the door and you step outside, you'll feel shocked.
Yeah. Okay. So it's like lightning.
Yeah.
So in a sense, lightning is the electric part of the EMP. It just doesn't have the magnetic force, right?
Yeah, hang on.
Yeah. No worries. Yeah, I'm starting to understand it now. I'm starting to get it.
It's so dry in the wintertime because of the cold. We're minus 20 C right now outside, and it just sucks all the moisture out of the house.
Move to like a desert island, George. Come on, man, get out of there.
Anyway, so these are what are called static fields. Now, the situation is a little different when you have RF energy, RF signals like microwave, FM, AM, TV.
Like alarm clocks.
All these are time changing waves. You have coupled electric and magnetic fields, and your EMP pulse will be of this nature. Is like whenever you have an electrical discharge, like a lightning strike, you hear it on your radio. Particularly in AM
gets all
radio,
staticky or something.
Because a spark will generate a spectrum of electromagnetic energy. Well, when you look at Maxwell's equations and you solve them for electromagnetic propagation, what we call TEM waves, transverse electric magnetic plane waves, and that's light is a member of that. That's where your TV signals, your cell signals, microwave, and all that are
your alarm
TEM
clocks do
waves.
that, right? Alarm clocks, like when an alarm clock goes off, it does that, right? Like the pulse like when if an alarm clock sets off, it'll give the pulse there, that the beeping. It makes things staticky sometimes. Like it's happened a few times.
There might be in the mechanism, maybe it's drawing some arcs or something because of contacts. Okay. Whenever you draw an arc, you will emit a TEM wave.
Okay. I'm seeing the difference now.
Like a switch. Sometimes you hear switches arcing.
Yeah.
If you see a little arc, electrical arc, it will generate a signal, or like your spark plugs of the cars.
Okay. Yeah.
Yeah. You have sparks in a spark plug, and without proper spark suppression, it just drive your AM radio crazy.
Yeah. Okay. Yeah. I've heard that happen before. Checking plugs.
Or like if you take a shaver, electric shaver or something, bring it near an AM radio, you'll hear it.
Yeah. Okay.
Yeah. Yeah. Well, what an electrical discharge will generate electromagnetic waves, and that's how Maxwell's equations were first verified. Is Hertz was the first one to generate and detect electromagnetic waves predicted by Maxwell's equations, and then Marconi took that and created the first radio transmission, communication transmission using that principle. He used spark gaps to generate RF signals. But anyway, if you solve the equations, you get a thing. There's many ways of solving these equations, and the easiest way to solve these equations is using complex variables and things called phasors. And with complex variables, you have an imaginary and a real part. And to satisfy Maxwell's equations, what falls out of these things are two things. One is called a propagation constant. It has a real part and an imaginary part. And the real part to it tells you the nature of the wavelength and the speed with which this signal will propagate. And it turns out that it's happens to be identically equal to the speed of light in any medium. And then that's the imaginary part. I'm sorry, the imaginary part. The real part of the propagation constant tells you how the signal is attenuated. Well, an interesting thing happens is you get something that's called a skin effect, and associated with it is a term called skin depth. And what that tells us is that any time varying signal, any TEM wave, will attenuate as it passes through materials, whether it be a conductor or dielectric, and it will decrease by 1 over E, where E is the constant 2.718281828, so on. It's a fundamental constant. And 1 over E basically works out to 37 or 36.8%, or 0.368, or call it 37. So every time a signal goes through one skin depth, a skin depth is the amount of material that a signal passes through to decrease by amount of 1 over E, or roughly 37% of its initial value. Say you have a boundary. The signal's coming in on the surface of the boundary at some intensity, and one skin depth, it will come out of that material at 37% less than it came into the material. That's the definition of a skin depth, is the attenuation. It's about 8.8 dB worth of signal loss in one skin depth. Well, skin depth is a function of frequency, the conductivity of the material, and the magnetic properties of the material, called its permeability. The larger the permeability, the thinner the skin depth, or the more conductive the material is, the thinner the skin depth. And also, as frequency is increased, the skin depth gets smaller and smaller. Well, what this tells us is that, say with a good conductor like copper, where you essentially have the same magnetic properties as free space or a vacuum, so the magnetic properties aren't increased in copper versus just going in air. However, the conductive properties are considerably enhanced going in conductor, because the conductivity of copper is about 5.7 times 10 to the 7th moles per meter, and air hardly has any conductivity whatsoever. Well, in a good copper conductor, the skin depth is about 8 millimeters, or about 1/3 of an inch. So that tells us that if you have a copper plate, that a signal, that skin depth of 8 millimeters, or 1/3 of an inch, is for 60 hertz, your common household frequency of signal. So something that low of frequency of just 60 hertz, which has a wavelength on the order of about 3,000 miles or so, it still has a skin depth, and it will lose intensity. It'll lose 37%. It'll fall to 37% of its intensity as it propagates 1/3 of an inch, or 8 millimeters, into the copper. Now, when you go higher and higher in frequency, the skin depth decreases as the square root of the frequency. So by the time you get up to microwave, say on the order of a gigahertz, like for cell signals, the skin depth turns out to be on the order of a micrometer, a micron, very, very thin. And that's why at these frequencies, you can create things called waveguides that rather than using metal tubes, you can make your waveguides out of plastic and just deposit a thin film of silver on it and make a very effective waveguide, because all of the signal at that frequency only travels on the skin of the surface, or within a micron or so, a millionth of a meter.
And as long as the frequency never gets strong enough, it can never affect the plastic. Or
well, the signal travels in the conductor.
Yeah, I meant the conduction of it. Yeah, that's what I meant. Yeah.
So this whole thing of skin effect is, it tells us that as you go higher and higher in frequency, signals tend to travel more and more on the surface of the metal rather than penetrate the metal. So to create an effective Faraday shield or Faraday cage, you just have to have material, say your copper, of sufficient thickness for a given wavelength.
Okay.
So by the time you get to microwave or up at cell signals, just about any copper plate of any thickness will essentially totally attenuate the signal, because you're going through many, many skin depths.
Yeah.
Say, to get through a millimeter, you're going through on the order of 1,000 skin depths.
Okay, and for every skin depth, at the first 10 skin depth, it's high, and then as you go down, it gradually becomes less and less until it has to spread out over everything.
If you go through 14 skin depths, your signal reduces to a factor of 1 millionth, or 1 part per million, which in terms of power is a 60 dB reduction, or in terms of voltage is 120 dB reduction. So it's a significant reduction. Now,
so when you build a Faraday cage, are you like, for when you're installing when you're putting a shield into a Faraday cage, is the shield more important? Is it the most important part of the Faraday cage?
Well, I'll get to that.
Okay. Yeah.
Part here.
Awesome. Yeah.
Is the wavelength, the frequency, and the wavelength associated is very important. Now, like when you have a lightning strike, the TEM waves that are emitted are fairly low frequency, okay? Whereas your cell signal is a very short wavelength. A 1 gigahertz signal has a wavelength of about 1 foot, okay? It's a third of a meter, which is about 300 millimeters, which is 1 foot. So the wavelength of a gigahertz signal is 1 foot, whereas you get down to, say, around 60 hertz or so, your wavelength is on the order of thousands of miles. Okay. Now, if you have holes in your Faraday cage, it becomes effective for static fields, as we previously talked about, but it's also effective for low frequency, long wavelengths. As long as the wavelength of your signal is much larger than the hole diameters, that cage behaves as if it has no holes in it whatsoever. That's why copper screens are so effective, very effective Faraday cages at low frequencies for ham radio and stuff, like, at megahertz or 28 megahertz, 10 meter band or whatever. You can use a copper screen to be an effective Faraday cage. It doesn't have to be a solid copper sheet.
Okay.
And the same thing like with your microwave. If you notice that the front plate of your microwave is, you have little round holes so you can look inside the microwave and see the food cooking.
Yeah.
Well, the frequencies of the signals in the microwave cooking is a few gigahertz, around 4 gigahertz or so. And the wavelength is much, much larger than the holes in that front metal shield. So the signals do not penetrate. The RF from the microwave cooking does not come out and harm you, because that's acting like a very effective Faraday shield. However, light, which is also a TEM wave, has a very, very short wavelength. The wavelength of green light is 532 nanometers. Okay, that's a half of a micron, basically. Whereas the holes in this shield in your microwave oven is on the order of about 1/8 of an inch. That's about 3 millimeters. And compared to the wavelength of light, that's like there's no shield there at all. It's like a big gaping hole to a TEM wave of light. So it passes through and you can see the food. However, the wavelength of the microwave signal that's cooking the food is much larger than that hole. So that shield effectively blocks the microwave signal from escaping and, cooking you.
Okay, I'm sorry. Yeah, that's what I was just about to ask. If those holes weren't there, what would happen? But yeah, guys.
Yeah. Now, an easy way to demonstrate this is like in modern build. Oh gosh, I'm so dry.
Yeah, no worries.
Excuse me. In modern building construction, where you have skyscrapers, where you have a steel I-beam superstructure, where you have these beams, steel beams spaced, a certain amount apart. Well, this acts just like the same sort of shield that you have on your microwave. You have holes in between, the spacing of these beams create a big hole. Well, your microwave signal and your cell signals pass through rather easily because their wavelength is much, much less than the spacing of these girders in the building. However, AM radio is not. And you have a cutoff frequency below which signals below that frequency will not pass through those girders. And if you ever notice, take an AM radio sometime into a building, a skyscraper, and you will notice that the signal essentially goes away, whereas FM or your cell signals will pass through without any attenuation whatsoever. That's because of this whole idea of whether or not you have an effective Faraday cage. That building becomes an effective Faraday cage for very, very low frequencies, which have long wavelengths like your AM radio signal, but it's transparent to cell signals and FM. So that's why I was saying earlier that we're both right, we're both wrong regarding the car. The car would block out AM radio on the inside pretty much, but let your cell signals pass through as if it's transparent.
Yeah, okay. I understand now. Yeah, I definitely see what you're saying. And what you were explaining had nothing to do with the magnetic pulse of it. So, yeah, okay. I see exactly what you were saying.
Now let's get to that part.
Okay.
TEM wave, transverse electric magnetic. What that means is you have coupled electric and magnetic fields associated with the RF radio propagation or light or your cell signal. Okay. Now, Faraday cage blocks the electric component of the field, but it is not very effective for blocking magnetic components. You could take, say, a solid copper pot, make yourself a solid copper sphere, put a steel ball bearing in there, and take a magnet on the outside, and you could move that magnet around. That Faraday shield cage is not going to block the static magnetic field. It's just going to penetrate as if it's not there. Okay. Now, however, when you go up into RF propagation, where the electric and the magnetic fields are coupled, what basically happens is the changing magnetic field will create an electric field. This is called Faraday's law. Yeah. And a changing electric field will create a magnetic field. This is called Ampere's law. These are two equations of Maxwell's equations.
It's literally how like RC motors are built and create power and everything, or transfer power, I guess you would say, right?
Well, Faraday's law is
that's what
used for power generation, whereas Ampere's law is if you pass a current in a wire, it creates a magnetic field, and you bring a compass near a current carrying wire, it'll deflect the compass needle on the compass. This is called Faraday or Ampere's law.
And this is part of the explanation you were having earlier with the iron. Right. Or the molten.
Now, Now, what's going to happen is as you go up in frequency, your TEM wave, you start generating to broadcast an RF signal. The way an antenna works is you accelerate electrons down the conductor. When you have accelerated charge, it radiates. And that's basically how an antenna works, is you're accelerating electrons up and down the metal elements of the antenna, and that causes radiation. So you initially start with an electric field, changing electric field. A changing electric field will create a changing magnetic field. That field, in turn, changing magnetic field creates an electric field. The changing electric field creates a magnetic field. This goes out at the speed of light. And this is how propagation, RF propagation occurs, is you have a changing magnetic field, generates a changing electric field. That changing electric field generates a changing magnetic field. So you have this whole chain of alternating electric magnetic fields. That's what's being propagated outward at the speed of light. Now, your Faraday cage could be effective at very high frequencies, because if you start blocking the electric field, no more magnetic field gets generated. So you essentially stop the field if it's short enough wavelength, with your Faraday cage. But at low frequencies, things are a little bit different. You have what's called the near field, which some people refer as to the Fresnel zone, and you have the far field. How RF propagation behaves depends whether you're in the near field or the far field. Now, in the near field, like when you're nearby, or most of the signals that you're going to receive are in the far field. We generally consider we're in the far field if we're outside of 10 wavelengths of the source of the electromagnetic propagation. So, for microwave, say at 1 gigahertz, by the time you're 10 feet away from the source, you're in the far field. Okay, you don't have to worry about the near field consideration. So, for all practical purposes, for most RF radio signals out there, you're in the far field. So, if you go low enough in frequency,
nigger. Hang on. You're pathetic. It's pathetic, P. Mars. Are you done?
A lightning strike generates low frequency RF energy, not high frequency. You have a whole spectrum of frequencies that are generated, say, on a lightning strike or any sort of spark, but the amount of it falls off dramatically at the higher end of the spectrum. As you start getting up into the microwave region or whatever, you don't get much RF energy being generated from a spark. Okay, or a lightning strike. So in the sense of a lightning strike, you consider that the RF energy is long wavelength, low frequency. So now you have to worry about the magnetic field portion of that, because low frequency magnetics are extremely hard to block. And in fact, they don't attenuate the same way electric fields do. With electric fields, you have this skin depth, and as the signal propagates into a good conductor, the signal gets attenuated. And if your conductor is thick enough, none of that signal, for all practical purposes, ever emerges outside or through that conductor if it's of sufficient thickness. Magnetic fields don't do that. Magnetic fields don't attenuate in that fashion. And the only way we can really effectively block magnetic fields is by a technique we call shielding. And what you do is you use ferromagnetic materials, things that have a large mu being the permeability of the material, like ferromagnetics, like iron, cobalt. They have very high permeabilities, and the magnetic flux will prefer to flow in these materials rather than in air. So what you do with magnetic shielding is you use these mu metal type materials, iron, steel, cobalt, whatever combinations. Mu metal, it happens to be a very special ferromagnetic material that has a very, very high permeability. So what you do is you redirect the lines of flux away from the sense.
All right. Well, thanks, PMars, for fucking that up. Give me a second, because guess who fucked up the hangout? Boy, PMars. Yeah, I always knew you were an asshole, PMars. I'm gonna go over to Discord, because now I know he can't get there. So give me a second, guys. That's pretty pathetic, PMars. So, yeah, George, if you are hearing me, go to... Let me see. I'm gonna go to the bunker. I will invite George over there right now. Z-switch. Yeah. Go ahead and invite George here. And I'll put it on the screen for you guys so you guys can get back to it. Hey, PMars fucks up another hangout. You must be so proud. Yeah, George, if you can hear me right now, I just sent you a link over to the Discord. We'll just do it from there. There we go. Get those up there. Turn on Discord one. There we go. So let me go ahead and turn everything else off. And we'll wait for George. If you guys want to join the panel and have to talk about what George was talking about, come and join. I do apologize. We had to end it that way because some people are fucking assholes. But hey, that's what we expected out of a PMars anyway, right? So can't really blame anyone but ourselves. Myself. Let me see where everything is, because I don't know why it's not showing. Discord. Alright, yeah. I gotta do all that other shit. Give me one second, guys. I'm setting up the Discord now. The Discord way of doing it makes it easier for me to see everything. There it is. Alright, we're good to go there. I got to change my audio stuff. Oh, it's already set up. Perfect. So yeah, I'm over on the Discord side. Hopefully George got the invite and he'll come back and explain things. Other than that, again, I didn't understand a lot of things that were entail of a Faraday cage and EMPs. So I do appreciate George doing that. What I'm gonna do is definitely cut out the George part and upload it as just a single explanation for it, along with having this, so it'll be work out that way. The whole point of using the Hangouts was basically to see the quality and of my connection and everything. I'm gonna use that for the MMA stuff. But yeah, going with that until George gets here, or we'll see. What I want to do is tonight. What I'm gonna be doing is I'm gonna do the John Jones Dominic Reyes fight. I'm gonna do a replay of it. I'm not sure who all saw it. If you guys saw it or I've talked to you with it, you know exactly what I'm going to say about the fight. But I'm going to do a replay and a review of the John Jones Reyes fight. And if you do want to do that, the link is in the description for the MMA server. I'll be doing it there. And then yeah, it'll be fun. We're just gonna replay it and then watch it and talk about it. Stop it halfway through certain points and just BS, and just gonna be hanging out and talking about the fights that happened prior week. Thank you, Jose, for last night. Jose stepped up and found a link for the fight nights. I don't know why my ESPN wasn't working. Kind of frustrates me. I did email them. Gotta check that too. But tonight I have the replay ready to go. I'm already looking at it, so that's not gonna be a problem. But so we're gonna be doing the review. If you want to do that, join us. If there is more than 10 people, I'm going to open a hangout for that, and then right off that, I'm going to just basically make that a viewing platform for the MMA stuff that I've been doing lately. But yeah, like I said, we'll wait for George to hopefully get that link. If you want to join I think I took the link off of. Yeah, because I was going to use the Hangout, so I took the Discord link off the out of the descriptions. My apologies. So let me put the link in here right now. And this will get you into the Discord panel. There we go. Now we're good to go. Now we are stupid proof. Let me see what's going on in the chat. And again, I'm pretty sure if you guys can find Rumpus, tell his bitch ass to come over. I don't mind. I'll have that discussion with him because I'm not hesitant. I don't mind having that conversation to his face like a actual man does. Rumpus, fucking pussy. Let me see. I'm trying to get everything back organized now that I'm not doing it that way. There we go. Now we're good. Yeah, I'm not sure if you got it or not, but yeah, Charlie, I found a bunch of these videos. They're pretty badass. I like them. That whole, the nature look phenomena that happened that are awesome. I see Gleem is going at it with Barney. I don't really know what they're talking about. I was listening to George. Yeah, it's one of those things where I think that a lot of these people have been in the discussion so long that the second someone doesn't just sit back and shut the fuck up, and they start asking questions or want a better explanation for something, they're assuming an attack. But I'm definitely not. I think it's Australia, if I remember correctly. Angle of attack. But realization is what I was doing is 100% legitimate. I was asking a question, I was trying to get an understanding of it, but people are used to attacking, and that's a big problem. That's kind of why a lot of the people that did the attacking are also the same people that on a regular basis get told to, take a breather, stop talking so long, stop doing this, stop doing that. And that's just reality of it. Like I said, Druss is my boy. I like Druss. I have no ill will against him, but it pissed me off that he had done that. He also, that happens in other places. It doesn't help a discussion when people want to jump on one person, especially if you're assuming why that person is even saying something. You're going to jump at them and be completely wrong for it, like everyone was. I was asking a simple question. No one should have jumped on me because I was asking for help, not trying to deny shit. And that's where the problem started. That's where I think issues are when it comes down to it. Yep. I don't know if George is going to come in, so if anyone wants to join, we can change the topic. I don't mind. We can talk about any topic. We can keep talking about the same topic. But all I know is I wanted to get that out. I wanted to stream and make people understand what the fuck happened the other night. In terms of what actually happened compared to what dumbasses like Rumpus come on and say. Because that shit to me is a joke. Rumpus is a joke. Let me see here. I'm trying to find some stuff that I wanted to show you guys. I don't know where I put any of my files because I wasn't expecting to do this. I see your message. Yeah, I don't care about Astro Rex. Astro Rex is a very angry person who has a lot of personal issues that he keeps to himself but projects to everyone else. And that's how it is for real. So, Astro X, you need to breathe. Maybe go get a spa, go slap an ass or something. I don't know. Anyway, let's see. Why don't you fucking join the panel, Davros? Or are you over there on the shield still? Traitor. Just kidding. Just kidding. Got jokes. Let's see here. I'm trying to message George again. What up, John? Yeah, Rumpus is a funny person. He's it's like he wants to be someone predominant, but he's really not. Am I a psychologist now? No, Astro, but I've known you long enough to know your ass got fucking issues. Let's keep it real, Astro. Don't fucking lie. You know damn well you got them. Yeah, George. Yeah, he did. He crashed the hangout. I'm over at the Discord. I sent you a link in the. I put a link in here, and I also put a link in your messages on Discord. In your messages on Discord, there's a link again if you want to join. Continue on, and if anybody wants to join on, you're all welcome. Yeah, but yeah, George. Unfortunately, he was. But no worries, Dave. I was just messing around with you. Yeah, there he is. George is here. I didn't say Rumpus was funny. I said he acts funny. Let's make sure you can talk. Oh, there. What's up? There you go, George. You should be good to go now. I'm sorry. I didn't realize you didn't have the panel roll. There you go. You should be able to talk now. You may have to come back, leave, and then come back in, though. Try that. But like you have all the roles now. I forgot this first time you were on the panel. Yeah. But yeah, I want to thank George because when George, I can't. If you're trying to talk, I can't hear you. Back out of the voice chat and come back in. I gave you the proper roles, but sometimes you have to refresh. So just leave the voice chat and come back in. Let's see here. Oh, Astro Rex, you're just getting personal now because I'm correct. I just messaged George to try exiting the voice chat and come back in because I just gave him the role, so now you can be able to talk. Yeah, he's back. He just came back in. So give him a second. Minutes who says, I realize that the clown is a different breed. I'm sorry you have to deal with the shit. Regardless, it's not cool at all. This ain't yeah, exactly. It's one of those things where it's just everyone's so ready to pounce that it shows, right? Like it really shows that something's up because it's frustrating. It's one of those things that I noticed right away when I left Flat Earth that it wasn't going to be easy to get answers because now when I ask questions, people are going to act like that. But it's here nor there. So let's see. Oh yeah, no worries, no worries. If you didn't hear me, try leaving the voice chat and come back in, George. Then you should be able to talk. I don't know why, because right now it looks like you're muted. But if you need a minute, no worries at all. No worries at all. And again, if you guys haven't, check out Channel Q's latest video, Moon Matrixes. It's a pretty badass upload she made. It's funny as shit.
Is that working now?
Yeah, I hear you. Perfect. There you go. Sorry about that.
I let Con in. He came over and he was kind of mad. I was on the computer and he put his chin on the keyboard. He's learned that he can crash my system.
Dogs are smart. They know what's up. Yeah, did you want to finish? You just got started getting into the magnetic aspect of it.
Oh, let's see. Well, like in your TEM wave, one of the important considerations again is wavelength and frequency. It's hard to shield against low frequency, long wavelength magnetics. They don't attenuate going through materials like the electric fields do. The electric fields have a skin depth associated with them, whereas low frequency magnetics do not. And the best you can hope to do is divert the magnetic field away from the victim or the sensitive electronics. And you do that by using these high mu materials like mu metal or some cobalt nickel combination type materials, and all you do is you divert the areas of sensitivity.
Okay,
so you basically redirect the magnetic field out and away and around from where you want it to be. Now, the situation is different at higher frequencies because you have these coupled electric and magnetic fields. You know, a changing electric field gives rise to a changing magnetic field. That changing magnetic field gives rise to a new changing electric field, and you have this chain of electric and magnetic changing fields, one giving rise to the other. Well, if you stop the electric field at some point, like with a Faraday cage, then you can stop the high frequency magnetics, because once the changing electric field is attenuated and stopped, it can't generate any new magnetic field. So you essentially block your RF signal if it's sufficiently high in frequency. So when you have things like sparks and lightning strikes, is these generate low frequency RF energy, RF fields. And you don't have a wide spectrum of frequencies being radiated from like a lightning strike or whatever. You hear it on AM radios, because AM radio, you know, at a megahertz is a fairly long wavelength. The wavelength of 1 megahertz signal is 300 meters. That's a very long wavelength. But there's very little, you hardly hear any lightning strikes, say up in the FM band at 100 megahertz, or definitely not on cell phones, because there just isn't much radiated electromagnetic energy from these types of things. And that's the kind of category your electromagnetic pulse would be under. Is it's primarily long wavelength, low frequency electromagnetic waves. So the magnetics can penetrate. It's associated with it, with this EMP type pulse. So the situation is different there. And, you know, a Faraday cage with holes in it, i.e. your automobile, would not be a very effective shield against an EMP pulse, because it's primarily long wavelength, low frequency, and so these are going to penetrate.
Yeah, but okay, I see. I 100% getting the car explanation and where you were at in the explanation of a car. So okay. Now I definitely see it. What you were trying to say and where I came in on it.
Yeah. Well, see, the thing is a Faraday cage is not effective across the board for all frequencies.
Exactly.
Now, the one that would be, of course, is, say, a good conductor like pure copper of sufficient thickness. If you made a Faraday cage without any holes, a box made out of copper, say a 1/4 inch thick, there's going to be very little that could ever penetrate that.
Yeah,
because
too
the
much
skin
surface.
depth.
Yeah, too much surface to expand on for it to actually penetrate it.
Well, it just depends pretty much of the frequency range and the situation that is under consideration. It's kind of like this argument that was on Jose's show about a week ago regarding open and closed systems. Well, to the purist, a closed system or an open system, a closed system does not allow any mass transfers of any significance. For all practical purposes, something like the Earth could be considered a closed system because the mass transfer, mass leaving the Earth or coming into the Earth from meteors and stuff is so small and so insignificant compared to the total mass of the Earth. Mass of the Earth is about 5 times 10 to the 24th kilograms. So in that sense, we say, for all practical purposes, it's a closed system. But to the purists, it's an open system because in the purest definition of closed, you do not allow any mass transfers, no matter how small, even if it's an electron. Even the mass of an electron, in the strictest definition, if you allow one electron to escape into the environment, you have an open system. But in the practical sense, no. And the same thing with these Faraday cages. To a purist, you need to have a box that's seamless, has no holes, that is totally enclosed. And but if you go up, if you're at sufficiently low enough frequency, you could put holes in it and it'll still be an effective shield or an effective Faraday cage. Just like I was saying earlier, you can use copper mesh, like a copper screen that has holes, and you can see through it because the light will pass through, but the RF signals at around 10 megahertz or so will not pass through it. So it's an effective Faraday cage. A copper screen is effective Faraday cage at 10 megahertz, but certainly is not at a gigahertz or for cell signals.
So this may be okay. So a nuclear weapon sets off will create an EMP.
Mhm.
A suitcase made EMP device only could maybe hit a block, right? I think that's about the range, a biggest one it can.
I don't know. I haven't really looked into it. It would depend on the size of excuse me, the size of the nuclear blast.
Yeah, but then,
and of course, one of the ways. Go ahead.
I was going to ask because one of the big things that a lot of people were talking about with the ICBMs was North Korea using one, but not have a nuclear warhead. It'd be a EMP device. So, but as far as I know, a nuclear weapon, shot in what do you call it? Explodes in the sky, creates an EMP field that propagates from it. How does that work?
It's just like any antenna. The higher up you are, if you're up a few thousand feet or so, you're going to have a lot better coverage because you essentially have an antenna that's way above the Earth, so it propagates over
more surface.
A good part of the Earth because your line of sight isn't being hid by the curve of the Earth. Like if you're down by the ground, a lot of the RF propagation, it will diffuse or refract over the curve of the Earth to a certain extent, but not, indefinitely. Whereas if you're up high, you have a much better coverage in the range, you
Yeah.
know, so to blow off an EMP device, you're much better dropping something from a plane, blowing it up, you know, 3,000 feet up above the ground.
Yeah, that's what they were saying. I think in an EMP attack, I think they're saying at 300 miles, 1/3 of the United States would be able to be hit by it or feel the effect of it, I guess. That was just kind of one of the, you know, the if this happened type things, because they were, what essentially I think they were talking about was the United States grid system that we have, and how it needs to be upgraded, because if, say, you know, there was an EMP attack, we'd be screwed because of how the system is set up, basically.
Yeah, well, that happened to us naturally. It wasn't an EMP event, but it was a solar event.
Solar, yeah.
This was, about 20 years ago or so. It triggered some
I think it was about 30.
breakers in Toronto, I think it was, in Canada, and then it just went down the East Coast, breaker after breaker. What happens is once a few breakers get thrown, then the grid shifts the load, and eventually what happens is too much of one system is taking too much load from other systems that went down, and you have this domino effect occurring.
Yeah. It's amazing how that happened. And I've read stories about that. Because I know, I guess apparently we're always being hit by these waves, but again, like you were saying, the magnitude matters essentially, and we're not hit by nothing comparatively. So, but what the magnitude of, say, of a natural event like that, is that anywhere in comparison to like what a nuclear weapon emits?
I really don't know. I
Yeah,
haven't looked into the whole EMP thing. It's a different mechanism. That wasn't an electromagnetic type event. What that was charged particles causing lines to arc over, and then throwing breakers. And then because of load sharing, those loads got from various cities like New York got shifted over to other portions of the grid that couldn't handle the load, and so on. It just kind of rippled on down the East Coast.
Okay, so when we're talking EMP effects, it's completely different than an EMP device. Am I kind of correct on that?
Yeah, well, that wasn't an EMP event that occurred. That was a solar flare event.
Okay, so
you know, it just overloaded some of the circuitry up around, I think it was around Toronto where it started, and it just kind of overloaded, and then because of load sharing, it just rippled on down. That wasn't an EMP sort of thing that was inducing high currents into the lines that caused the lines to overload. You know, an EMP, what you're basically doing, it's a Faraday law type effect, is you have a changing magnetic field that induces currents into wires, and because of the pulse, the magnitude of the pulse, and these changing magnetic fields, you can generate very, very high currents in the circuitry and essentially burn out some of the circuitry because of the current overloads. EMP device would be one that's more likely to damage equipment rather than causing these types of temporary overloads. You're actually going to burn out devices.
Yeah, the processors, right, of it, the processors.
Yeah.
Okay, so
the processor wouldn't even have to go. All you'd have to do is just kill some of the I/O ports, and your phone is screwed.
Well, essentially, if we had an EMP attack, essentially it would do that to our ATM, or basically our whole system. I was trying to say something.
Well, to tell you the truth, given modern day electronics and how we design these things, I don't know if it's as big event as people are worrying about, because I mean, the electronics that we have now and the sorts of designs that go into our electronics are pretty robust compared to what they were 30 years ago. Like, even though you have plastic cases, and plastic does not shield at all. But what you do is you flame spray the insides with a conductive paint, and that gives you shielding. And the devices, the modern ICs these days, are a lot less susceptible to failure than the IC devices of 30 years ago. What goes along with these smaller geometries are better protection circuitry. You can add a lot more protection circuitry at the IC level than we ever were able to 30 years ago. So a lot of these devices semiconductors are very robust these days.
Yeah, and even in that event, there's always a system that everything's backed up to, compared to 30 years ago when, everything backed up wasn't even, quite as possible as it is today. So the restart wouldn't be as significant as it would have been.
And the devices, to radiation or EMP, electromagnetics, even just like cosmic radiation stuff, like going through the Van Allen belts or whatever, the electronics are a lot more robust than it was back in the 60s, like with the moonshot back then. Our electronics now can survive through going through these radiation belts a lot better than they ever could 30 years ago.
Yeah, you just give it the shielding it needs to work at least sufficiently, and then it becomes less of a problem, where before we didn't understand what it took to shield it.
Well, the thing is the radiation hardening of the electronics is a lot better today.
Yeah,
a lot of it just comes for free too, because of the device geometries that we're using now compared to back then. We're down producing ICs on the order of 7 nanometer line widths and stuff now, whereas 30 years ago you're talking you might have been somewhere around a few hundred nanometers. So along with the smaller devices, the smaller amount of areas that go into making up your CMOS transistors and your memory cells and stuff make it that less susceptible to these radiation events.
I see what you're saying.
There's just not as large a footprint, say, in a memory cell or a transistor in today's devices, ICs, as it was 30 years ago. So devices were a lot bigger and they got a lot more dosage. It's the total dosage of radiation that becomes important, not necessarily one particular event, whether it be high energy or not. It's the total dosage that kills the electronics.
Yeah, it's the what is it? The time it would take to recover versus. So I forget. Yeah, I see what you're saying. Though I know exactly how.
You can survive a high energy. You can survive a very short high energy radiation event better than you could a long-term medium radiation event. It's the total dosage that becomes
saturation. Important.
Intensity times time, that total dosage that's important.
Yeah, exactly. Yeah, the saturation of it is what it is. Does it have enough time to saturate?
It's kind of a cumulative, kind of like mercury poisoning. It doesn't get your cells don't get rid of mercury. It just becomes accumulative to the point where it eventually kills you.
Damn. This mercury sounds so dangerous, but I keep hearing people talk like it's not dangerous. It sounds dangerous.
No, it's not that dangerous. Cripe, as kids, I remember in 4th grade, we used to play with mercury all the time. We'd coat our quarters with it, and we'd rub our fingers and stuff in the mercury. You're not going to die right away. It's the mercury fumes that kill you.
Okay, because I remember Toady was talking about it, and I was just like, who the fuck plays with... I was a kid once, and I never in my life played with mercury.
Oh, yeah.
This is the guy that goes to... the guy that goes to lay-bys. Come on.
That is true.
So, this thing with mercury, like George said, it's the fumes from the mercury that hurt you. But accumulative effects, think of arsenic, right? It's actually an element, right? It's on the periodic table. But you can have low doses of it and it does fuck all to you. But if you increase if you increase the amount of times you have those dosages, it'll kill you.
Yeah, it's like that one dude, the uranium eater guy. I used to tell people that it's like the dude's not eating very much, and over time he doesn't have enough time, or he's not taking enough for it to actually affect his body. The next time he does another presentation or speech doing that shit, his body's already basically dissolved it completely.
His pee probably glows in the dark, though.
Does it? So if you eat like small doses of uranium, your pee will become green?
Well, it depends. Depends on which what parts of that element he's releasing through his intestines.
That's not good, because there's this one vitamin pack from Kirkland. If you take the vitamins, you pee neon green for half a day.
Glow in the dark too, huh?
Yeah, I haven't checked, but my girl would be mad at me if I checked. But I just gotta see if it glows in the dark. Splatter, splatter, splatter. That's all I need for her to be able to see where I missed.
Or you're leaving her a path to the toilet.
Yeah, exactly.
Doesn't have to turn on the nightlight.
Nah, F that. I can blame it on my son as long as I don't have a path to me. Yeah, but it's weird. Vitamins do that sometimes. That's like, for a long time, that's the only way I was able to take vitamins, because I don't like taking pills. It was just the idea that, hey, I could take a pack of pills and next piss is going to be neon green. And I'm sorry, even in my 30s, that shit is still funny every time. Every time.
I'm just going to comment to people in chat. I know uranium doesn't glow in the dark. We're just making fun of it. Take some radium.
Yeah, well, think about that kid that got busted for trying to build a nuclear reactor in his mum's garden shed. Look at what happened to his face.
That was in New York, right?
Yeah.
Wait, what happened to his face?
What happened to his face? Yeah, because he was stealing all the shit out of smoke detectors.
Huh? Wait, there's uranium in smoke detectors?
A little bit.
What the fuck? Where? Wait, do we want to say where? Maybe we should hold off on that.
Because he got busted because he stole a whole bunch from, I think it was a construction site or somewhere. Like, it was a whole heap of new houses that had been built, and they were in the container or whatever at the site. And
how many
stole the whole box.
Would you need to be useful?
Well, the fact that he got found out by the FBI, obviously they tracked the radiation signal to the house.
Are you serious? Damn.
I'll find the
video.
Easy.
It's fairly easy to track radiation from uranium.
Wait, it's
pretty hard to hide.
Yeah. Is it? What was I going to say? Damn. I forgot.
Look him up on YouTube. There's news footage and everything about it. And he's still fucking doing it.
I don't get what. So wait, how does my smoke detector have a rate something that is? I don't get it.
There isn't. I mean, that's kind of a urban legend. I think there isn't enough in the smoke detector, no matter, even if you had 100,000 of them, probably to amount to much.
Because I was like, that's like that same thing where people are like, collect old computers, you can get gold out of them. I'm like, I look at my computer, there's no fucking gold in there.
Well,
yeah, that's what coats
there
the
used to
tracks.
be in
That's
the 80s. In the 80s, back in the 70s and 80s, a lot of the boards, PC boards, were coated in gold with what we call thick gold. they put about a micron of gold. And the reason why you use gold, like on edge connectors and stuff, is it doesn't oxidize. It doesn't
Yeah.
tarnish and oxidize. And still these days you'll find thin gold put on certain edge connectors, but definitely not on the PC boards. Now we use nickel plating on PC boards.
Yeah, you'll find it's a silvery grey colour.
Okay, so it's about these old computers. So when these collectors find enough of the old computers, then they're able to get an actual return on the gold. That seems like it would take a lot.
You'd have to find things back in the 70s and 80s, like the old HP computers. HP back in those days, they gold plated everything. Our PC boards, all the traces, all the edge connectors, everything was plated with thick gold.
And that was the idea to protect it as best as possible, right?
It was just to keep the traces from deteriorating. Is you can have issues of, like in a salty environment by the seashore, it'll eat into the copper. And by gold plating it, you stop that. You arrest those types of corrosion.
Yeah, now people are breaking open TVs. They're breaking open TVs to steal all the copper.
And Gleem talk on the GPS live chat thing on stream. I'm confused.
Gleem and GPS still talking about GPS signals. Fuck's sake.
If you Barney, if you're asking if you in GPS and your Gleem could have a convo on the stream, more than welcome to. Yeah, come on. I'm not sure if that's exactly what he meant, but yeah, absolutely.
Just a quick thing, Sean. Just back to the electric fields, right? What George was talking about is shorting things out. Now, I know you've done a little bit of welding, but have you ever seen what happens when the stick sticks to the steel and you watch that rod heat up and then you blow the switch?
I'm
That's what happens when you overload the current. Because what you've done is, because the amount of energy that you're putting through that rod increases, and because it's earthing, but the thing is you're concentrating the heat in that rod, it then sends a signal back through the actual welder, which then trips the 10 amp or 15 amp fuse.
You seen my camera at all?
Think I have before in a upload, but I don't remember it.
Oh no, I'm saying, are you getting a live video feed from me right now at all?
Oh no, not right now.
Because I was going to show you, I have an example of some of the PC boards that we made back in the 80s at Hewlett-Packard. There was particularly this one construction called fin straights that were used on the new computers back then. And the way these were made is you started with a solid copper core to carry the heat away from the processor and the memory chips. I mean, these things were run at really high frequencies, high power, and you had to really suck out the heat out of these things quickly. But the way these were made was with plasma etching and sputtering, and you'd sputter. You'd start with a copper core, and then you'd lay a Teflon coating on it, and then sputter gold on top, and all the connections were made with pure gold.
Okay. I see.
As an example, these are very pretty. I mean, I've got these boards. One board probably weighs a good half a pound, and this thing is probably 6 inches on the side, and it's just, the whole surface is just very pretty. It's all pure gold.
Okay, I see. I see what it is now. I was always like, is there like some secret chip in there with a stock of gold or something? They hit all the gold from everyone in the computers. It's so genius.
You salvage the chip. There's salvage houses that will grind down the boards, and because not only are you trying to salvage gold, you're trying to get the palladium and the platinum
Mm.
within the ICs. There's platinum and palladium also used besides gold.
And palladium is now worth more than gold.
Okay, but how many motherboards of that nature would you need? 2,000, 3,000?
Oh, no, not at all. Like from some of the signal sources from back in the mid 80s that Hewlett Packard made, on one of the main motherboards, you could probably sell one of them now probably for $50 for
Oh,
gold
shit.
reclamation.
Damn. That's amazing.
There's a
But, I
lot of
mean,
gold on these older boards.
so that's why people collect old computers. They just save up a little, get a few of them.
Yeah, you should see some of these old signal sources like the HP 3335. You open one of those things and there's gold all over in that thing.
That's crazy. And then there's places that probably, specifically do, remove the gold from these boards and shit for, the processing to begin or whatnot, to wait and all that. That's crazy.
Typically what they do is they put them in, they pulverize, they grind everything up, and then there's, they float it in a bath, and because
and
of
the gold drops.
gravity, certain, metals will
Yeah,
precipitate out before others.
It's like gold panding almost. Just like the idea of it, how it works.
Yeah. Exactly. And then that's the primary process, and then you put it into secondary processes where you use chelators that bind themselves with particular types of metals.
Yeah. Yeah, those are those more technical devices that like start separating everything. Like it runs through different tube separators, and then as it runs through a screen, the basically the outlets all are at different levels, so that once it drops to a different level because of its weight, they will then pass through an output that way to a screen or something, or a filter, I think it is. I'm trying to remember.
It's pretty hard to find a lot of these older instruments and computers now, because for the past 30 years they've been mining this stuff, so this stuff's been pulled out of the market, for quite a few decades now. So every now and then you might stumble across something, but it's going to be hard to find a lot of these older computers and instruments for gold reclamation anymore.
Yeah, 2013, and we're talking about what 40 years ago. These things were around. By now, what most people do is just chuck their computers. Really, a lot of people don't.
You'll
understand.
find a lot of secondhand computer stores have a lot of this shit out in the back. Or these old, even like I think 386 computers still had gold connectors and shit. So yeah.
Well, I'm pretty so in the recycling world, a motherboard is still worth money even today, though, right?
Well, a certain amount of motherboards will still have gold on the edge connectors. They use now what's called selective plating, is that you'll only plate like edge connectors in certain regions, and the majority of the board is plated with nickel.
Okay, yeah. Yeah, give me one, guys.
Hello.
Barney.
So
Hey, how goes it?
I got mixed up in the conversation between GPS and Gleem about GPS satellites. And we decided to move it on to stream, if that's okay with you.
Sean said that was fine.
So, Gleem, I'm fucking train. Just give me a second. I don't know if that's coming over, but I can't hear myself think.
I can hear you, but I don't know whether you can hear me.
I can hear you fine.
Brilliant. Okay. Yeah, cool.
So it was all cool until the part with decibels.
Yeah, it was more to do with the field strength. Could you imitate
I can hear you fine.
something?
Khan, you have sorry, George, you have some playback. Decibels. I can hear myself.
Yeah, it was more to do with the field strength.
George?
Imitate.
I can hear you fine. Okay. So, decibels.
Yeah.
Go.
Yeah, all it basically was the thought process of, can you replicate GPS, the whole satellite constellations, by using ground-based signals and reflecting it off of the ionosphere? Now, your valid point was no, because you would know the source. However, if it's a reflection and you calculate, let's say that the strength that you're actually getting from this satellite of signal, of whether you're getting it or not, you would be able to, let's say, triangulate using the signal strength that you are actually getting, dependent on what satellite you think that signal is coming from. So the whole question was, could it be replicated? I'm not saying it definitely is. I'm not saying 100%, but could it be?
So let's try to think up a way in which it could be replicated, right?
Yeah, exactly that.
Yeah. So if I knew your location, if I knew exactly where you are beforehand, I could calculate what the signals should be, like what the timestamp should be for you from those locations, and send you the information claiming that it's that. However, it would have to be cast directly to you without anybody else being able to sniff those signals out.
Sure,
right?
sure. No, I do
So
get that. Yep.
I need to know where you are. I need to know that you're listening. And I need to send it in some way of broadcasting, which isn't broadcasting, which is undetectable to everybody else except for you. And then I would need to do that for every possible receiver on Earth.
Yeah, I don't see that. I don't see how that would be the inverse. That would be the inverse of the way I think. If you can follow me on this thought pattern, I have a network, a honeycomb network, let's say a square country, honeycomb networked up, and I've got antennas in every single joint, let's say, of that honeycomb, of every single hexagon. Now, they are constantly transmitting a particular location. Now, no matter where I move with my device, I am hitting or getting, should I say, certain signals from certain masts, which allows my device to then multilateralize or triangulate where I am within that honeycomb to a certain degree.
But so, they're broadcasting their locations, right?
Yes, and that would allow you then to identify your location based on 3 or more.
Yes. Yes, that's true.
So now remove satellites from that issue. Or
the counter argument to that is that I can take a radio receiver, right, and tune it into the 14,000 megahertz, whatever it is, frequency, right, and pick up the signals from the satellites. And those signals are timestamp and location, right? Timestamp and an identifier which can be converted into a location.
Sure. Yep.
Right? So I can do it with a passive radio receiver so that nobody knows that I'm receiving it. And I can do pen and paper, literal pen and paper calculation, triangulation of where I am.
Yep. Okay. Yep.
Now, either in my calculation, I have to know that the system is being broadcast from ground, from those positions on ground,
Okay, I'm there. Yep.
Or those signals can be broadcasting that they're out in space, but then they have to tailor their signals to me specifically, even though they have no idea that I'm listening.
I think I get you there. I think I actually get you there. Because it would be for this particular mast, two different people would have two different signals to that same mast. However, that wouldn't replicate a satellite being up there. Is that what you're saying? Is that
Yeah,
what
so
I'm
the
getting from
mast
that?
is not sending out two different signals to different people. It's sending out one signal
The
to
same
everybody
signal.
who's listening, and saying same thing for the satellite, right?
Yeah.
But you need to know where the originator is in order to triangulate your position. So if the originator says I'm in orbit, but he's actually right next to you and he is broadcasting,
Mm-hmm.
then you will calculate your position to be within a couple of 100 meters from the satellite in orbit.
Yeah. No, I get that. I get that. However,
So they
if
could
you
be sending out they could be sending out fake signals, but in that case they have to know where my exact location is, and they have to know it. They have to tailor their signal to me. But that means that if you're 10 meters from me, then they have to send you a different signal than the one they're sending me.
See,
Because you're no longer triangulating from the positions in space, you're triangulating from fixed position on Earth as though you were triangulating from space. And the thing that you're measuring is the disparity in those timestamps. What is the difference between the signal from one satellite and the other and the third one? And that gives you your location.
Yes, that is my exact thing. So if we, let's say, just for arbitrary purposes, this is nowhere near anything like reality, but let's say it takes 2 seconds to get from a satellite up in orbit down to Earth. And it takes also 1 second to get up to the ionosphere and another second to come back down.
Okay.
So that's what I'm not getting. How could you not disguise, let's say, the signal? And even if you're next to it, the antenna is pointing up to the sky and sending it out to there. So you're still only going to get the secondary signal, let's say.
So if your precision was within a couple of 1,000 kilometers, you could do it that way, right? Or a couple of 100 kilometers, you could still do it that way. You could fake it, but if we're talking about, well, it needs to be within a meter of you, then you would either have to have a tower which is somewhere out at sea moving relative to me to stay in the right position and at the right distance as though it were a satellite orbiting Earth, which would mean that it's moving at thousands of miles an hour through atmosphere, like, at orbital speeds through the atmosphere, meaning it would just burn up.
To be relative to what it's getting at reality. No,
yes.
I understand that, and this is not more saying satellites don't exist. It's saying, can it not exist?
No, I've thought about it. There literally is no way you can fake it. The technology does not exist where you can broadcast something so that it is received by one receiver specifically.
reflected ray of radio wave. But I don't get why you would need an individual one for each individual person, because as you say, it's broadcasting the timestamp and the location, let's say. So if the timestamp and location for an antenna I'm firing directly up in the sky to then hit, let's say, the dome, let's go on that, but then as it hits the dome, it spreads out all areas, comes back down, and that signal, wherever that's come from, is directly from this location on the ground. That's the bit.
Okay, so maybe I can explain this way. You are more or less fixed to the Earth, right?
Mm-hmm. Yeah.
And the antennae on the Earth are more or less fixed to the Earth.
Sure. Yep.
The constellations of satellites are not fixed to the Earth. They are in orbit.
Yep. No, get that.
Some of them are in geostationary orbit. Some of them are in low Earth orbit. Some of them are in polar orbit. So their constellation keeps changing, right?
Yep. Okay. Yep. I'm following that completely. And you can't obviously keep moving the antenna on the ground.
And you can't keep moving the antenna. So those antenna can fake that signal. Like you are just receiving a radio signal. You don't know where it's coming from. So if at the precise exact time that you need to hear this number of a timestamp and this location in space, I can broadcast that from a tower that will reach you, right? But that timestamp needs to be timed to you receiving it as though it was sent from that satellite.
Yep.
Now, if somebody's standing on the other side of that antenna, right, then for them, it would have to be sent slightly earlier.
Yes. No, I fully understand that now. I do actually understand that.
So the signal has to be personalized to the receiver, to the location of the receiver.
Yeah, and I do get that understanding there now.
So no, it really cannot be faked at all.
I mean, could you not mask?
I could fake it for an instant for one person of a known location, and that would be a huge chore. The ability to pick it up passively with a passive device such as a car GPS makes it an impossibility. There is no such infrastructure, there is no such technology, there is no possibility to blanket the Earth, nor even a small area of the Earth with such a detection network that would locate things so precisely, nor broadcast them so selectively.
Yeah, no, cool. If you can just carry along down this other thought process of me, it spreads out all areas, comes that. Yeah, I just on that alone. Yeah, I think it would be a lot more difficult to, but I still don't think it's impossible to. So the reason being is that, let's say I originally put up, and they're all going to be in different times, obviously, 5 geosynchronous satellites and 10 which were put up in different orbits, various whatever orbits. Yep.
Yeah.
And the only differentiator on that, let's say the string that you receive back of the location timestamp, because it's not only just that, it is actually the actual ID of the Navstar, whatever the actual satellite it is. So could you not, let's say I have 5 dotted all around the equator, and as it goes around, it's still doing exactly the same job. However, it's just changing this ID tag based on time and pretending that there is something
that will reach you,
but
right?
it's receiving
but
this
that timestamp needs to be.
Do you get that? Do you get how I explained that? Or am I being desperate? Super desperate.
Okay, so I think we need to go one step back and work out how exactly GPS works, right? So when a satellite broadcasts its timestamp. It broadcasts its clock. Because of the immense distance, it takes some time to get to you.
Sure.
Right? And it will get, let's say that the satellite is on my eastern horizon. It will take less time to reach a person which is more eastwardly than me.
Okay, yeah.
Right?
Yep.
It will first reach them and then reach me.
Sure. Yep.
That difference in times when it reaches us, even though we're receiving the same signal, that difference in time reaching us is what tells me where I am.
Right, yeah.
That's how I calculate where I am. Now, if you have a broadcast tower standing between us, broadcasting that same signal, claiming to be on the eastern horizon, then there is no guarantee that it will first reach him and then me, nor that it will reach him with the appropriate time offset and then reach me with the appropriate time offset. So it needs to broadcast two different signals for us with the same timestamp.
Yeah,
and it needs to broadcast them somehow that I don't hear his and he doesn't hear mine.
No, see,
I mean, it's even worse than that. It's even worse than that, Barney, is what about the people that are located 90 degrees off axis from you? I mean, it's not just front and back, it's all around for 60 degrees. How are you going to have infinite number of timestamps?
Yeah. But what I was more thinking is that horizon thing you done in the simplest form is to put the actual transmitter nearer them. So then there is still a time differential between you and them in comparison to where the signal is going up and then coming back down.
Yes, but people are
first, but then you next.
Yes,
got a thought here.
Yes, if you have two guys whose feet are nailed to the ground so that you know where they are and that the tower is nearer to them than to you, you could potentially calculate the signal which would emulate as though it's coming linearly from that direction. But it's a 3D system.
Yeah,
so it needs to correspond in every direction, and also our feet are not nailed to the ground, so it needs to be able to work at any point, anywhere. Even if I was nearer to the tower and he was farther, if I walked up to the tower, it would still need to work.
Here's a thought,
they
Barney.
change path.
Here's a thought, Barney. You could have, say, a satellite that's moving in orbit that's transmitting a steady signal, and for everybody on the surface of the Earth, they're receiving a different timestamp, ever so slight, as that satellite is moving overhead. Some people, the satellite's receding. For some people, it's coming closer. Now, you could have a fixed tower broadcasting a signal through a variable delay line that would create the same sort of thing for one person.
Yes.
Now, of course, as we're talking about, we have how the heck are we going to implement this very complicated structure to create different timestamps for multiple receivers? And it seemed to me that that's going to take a very expensive system, a lot of push-ups.
Too much. That's
why do that? Why not just do something simple like orbit a satellite?
No, you are right. I will say that is definitely more work than what you would even bother with. Yeah. No, I get that. I do get it.
The allegorical origin of the GPS system was when Sputnik was sent out. He was sending out those beeps, right? Beep, beep, beep. Yeah. And some guys in the US figured out that they can actually triangulate its position from its beeps if they just measured when the beeps were coming from 3 different locations. And thus they proved to themselves that Sputnik is actually in orbit in space. And then they figured out that they could reverse the whole thing and have 3 satellites in orbit to pinpoint the location on Earth.
Yep, no, I get that. Yep.
And you literally cannot fake that, right? If you could fake that, you could also fake the Sputnik's position, and you could, like, you can triangulate. You can do the reverse. You can take signal from any one of those satellites from multiple positions on Earth's surface and figure out where they are just by listening to the same tick, to the same timestamp signal being broadcast in all directions. If it was a tower, you would then know that it's a tower.
Yeah,
Even if it was claiming that it was in space, even if it was trying to fake the signals, it would have to send a separate signal to each of those listeners to fake its location.
Yeah, because it has to be coming from the sky. No, I get that.
Yeah.
I do. No, I understand that. 1,000,000%. But anyway, just because both of you are in here, George and Barney, I've got a challenge, and you don't have to do it obviously at all. But Jose just showed a recent bit of footage, which is showing half a water tower where it should be completely behind the curve. And I've said to everyone in his comments, look, can anyone figure out or reverse engineer what the refraction would be required in order to unhide or loom up this water tower? Because literally it's one thing globe earthers saying to flat earthers, yeah, every time we say something's getting hidden, you just say perspective or flerspective. But it's the same on the opposite fence with globe earthers just saying it's refraction. It's refraction. But no one ever shows how much it would be. And
Of course, one could do it. You have to have precise geographical data and height data of the tower and precise distances between the observer and the target.
it's not precise. It's sort of like 23.3 miles measured on Google. There we go. That's as precise as you get.
Well, that's good enough.
Yeah, it's 150 height, and there's probably about 70 foot of it missing, but there should be 180 foot on Metabunk standard refraction.
How many? You said 20 some miles?
23.8 miles.
Well, I've actually measured looking across
Observer
to
17.
Canada. When I look across my bay here, 2.5 miles to Canada, on the other side, there's a railroad bridge that I can view, and I have in years past and monitored it as to its apparent position relative to the shoreline. And I have measured on days as much as 12 feet of looming over 2.5 miles. And elsewhere on the lake, last year, looking at fish houses out on the lake, there was one day where I saw a fish house a half a mile away loomed up twice its height.
See, this is a big thing, George. In your opinion, did that actual scenery move up? If you got one photograph at the same height and same, obviously, 90 degrees on your tripod, if you got them both together, would you have seen the horizon line loom upwards in the whole photograph, or would it be at the same level?
It depends on the temperature profile over the lake. I mean, if you assume a uniform gradient, then yes, that would probably happen. But I have photographs where I can show you that things have loomed up 2 miles away, but not at 6 miles away, or vice versa. I mean, you can have different temperature gradients and conditions over a long haul, like over 6 miles. I see things happening different in the foreground at 2-3 miles out from what I see at 6 miles out sometimes.
What about the inverse sinking? Sorry, Bunny.
That's okay.
What about what?
Sinking. Have you ever witnessed sinking?
I've witnessed, in a sense, in terms of compression, where the top of the object is fairly undistorted, but half of the object to the base is just extremely compressed together.
And that was, I mean, sinking, as I've read up on, it requires sort of like a 10-degree differential. So it requires something extreme, put it that way.
I mean, I've seen some rather extreme conditions, and they all seem to occur right around sunset, an hour before sunset, when, particularly in the spring, you can imagine that, the surface of the ice is always going to be at 32 degrees and at the highest temperature, right? It's ice. So during the days in the spring, when the sun, say in April, is fairly high now in the sky, the air above the ice can get extremely warm. It can get up to 40, 50 degrees Fahrenheit. And so you have extreme temperature differentials and gradients. And near sunset now, when the sun gets low on the horizon, the air starts cooling rather dramatically. So you had the lower air next to the ice upwards of maybe 40 degrees Fahrenheit, and then all of a sudden the air above it is cooling off dramatically as the sun goes down. And I mean, I've seen temperature shifts through the day as much as 70 degrees Fahrenheit between morning and afternoon air temperatures, and during those conditions, I see some rather weird things going on visually on the ice. I mean, you get these extreme compression where tall objects get squashed down to very, very small objects. Sometimes they get expanded. You get all kinds of weird refractive conditions occurring when you have these extreme temperature gradients.
Do you think then, by judging sort of like angular size at long distance, is even bothering worth it? Because you've got all
actually, that's what I'm working on now. I have one of the best natural laboratories probably that anybody has. Rumpus and I have been discussing this. And in my optical corridor, shooting out 6 miles across the lake unobstructed, I've got a number of islands that are spaced over that 6 miles, and I know exactly what their distances are. And then over on Franzen Island, which is 2.72 miles away from my dock, mounted on the bedrock is this 30-foot channel marker that I've gone and I've measured every aspect of that with a tape, carpenter's steel tape rule. So I know exactly the spacing between the members, the widths of the members, all their physical relationships. And I can sit and monitor it with my precision theodolite and measure these angular distance sizes and watch how they change over the 30-foot height. Look at what's happening near the base versus the middle and near the high. And that is what I'm engaged with now. I'm trying to quantify this more now with Rumpus, where I'm actually going out with my temperature thermistor array, measuring the air temperature gradient from the surface on the ice on up 20 feet in 30 centimeter steps, and then also measuring the angular sizes of the various members and distances between the members, the separation. So, trying to get some real hard analytical data on all this.
Yeah, definitely.
And that's what I'm engaged with now.
If you look in the Discord chat, I've just posted something from the Air Force Institute of Technology, and they agree with you exactly that. At the latter end of the day, sunset, things begin to loom up sharply, and then in the morning when the sun comes up, it starts to all sink back down again.
Right. Yeah, that's exactly what you see. Yeah.
And they recorded in theirs, they done it throughout the day and done a time lapse, a very slow time lapse, not any in depth, but once an hour or something. And they measured 9 pixels difference in the angular size of a building, or in the measurement of the building based on pixels.
I'm not doing photographs and counting pixels. I'm actually using surveying equipment where I look through the optics, and I can get things within 5 arc seconds doing it this way. It's very precise.
What optics are theodolite?
Well, what comes along with the theodolite? I mean, it's a 30
No, sorry,
color.
I was making. Yeah, so it's not a photograph. Sorry, you're not using any camera. It is a theodolite.
No, I take pictures of what I see, but
sure,
I actually measure with
Measure.
the theodolite measurement system. I can move the optical head in a vertical angle and have the digital readout tell me what angle it is with respect to the horizon or the horizontal.
Right, then here comes a big question for you then, and you put it this way. I think there is nothing that you can say other than yes, that is refraction. But I've just posted another thing, a video from Life is Short. Now he's just done a test over a still lake. Again, it is at the night setting, and it was only just done recently, at the beginning of February, I think. But it was nightfall, going into nightfall, because he set up his equipment. And how he done it is on one side of the lake, and the lake is only 400 foot in length. On one side of the lake, he put a light which was 63 millimeters above the water surface. And then he went over to the other side, and he only used a iPhone. So the aperture is obviously crappy in comparison to a normal photo. But he managed to be 1 foot above the water. And bearing in mind, there's only 1.2 millimeters of curve over 400 foot. And he's then dipped his iPhone case. So he's about half an inch from the water surface with his iPhone case, and he makes the actual light disappear from bottom up. Basically.
Yeah, well, that's something I will not do, is within the first couple meters, or at least definitely within the first meter above ice or water, you have this humidity zone that it causes extreme problems in terms of shimmering and unstable atmosphere. I'm typically making my measurements with my theodolite mounted at least 8 to 13 feet above the surface of the ice.
Gotcha. I gotcha. But so you would say that would be pure refraction effects then of him
right in the distance, yeah, because you're up above the humidity zone close in to the theodolite, where the atmosphere isn't going to be unstable like it would be in the distance.
You should see that video, George, and take a look at it, because where he starts, the light is a pinpoint source. And the closer he gets down to the surface of the water, the more diffused that light becomes. Yeah, it grows in size by, I'd say, a factor of maybe 10. So, it's very clearly demonstrating the amount of refraction you got sitting down there at that low elevation right above the water.
Yeah, that's really problematic, and I tried to avoid that, just like I did a couple winters ago when I mounted my observation point 13 feet up above the ice when I was doing my Bedford level target, and my targets to a tangent is to get up above that humidity zone.
So yeah, it was definitely refraction then on that, because I mean, I think that does display a lot of globe earthers, and you've got to admit, you've probably heard it yourself, that they're saying that there's no way that refraction or perspective can hide anything bottom up as it goes off into the distance.
Yeah, I don't believe so, but yeah,
that's it. I mean, you see, everyone's seen the refraction hide something from bottom. And you don't have to believe that it's not Earth curve that's doing it. It's only that refraction. But people just take it to the extreme. I mean, Lewis was one. You all know Lewis, obviously. He was basically saying you can never, ever, ever hide anything behind a band of refraction.
Oh, it's different. The thing is, when you see refraction occurring low to the surface, you get these distortions and and a lot of times compressions or expansions that just doesn't occur when you look at objects going way out in the distance and getting hidden by the bulge of the earth or of the water of the lake. Like when it starts, if I'm 6 feet up making my observations as things go out 6 miles or whatever, you get real nice images of things being hidden. And whereas in what you're talking about, you tend to see a lot of distortion and wiggling and shimmering going on, or compressions, a lot of distortion. And you don't get that when you don't have those sorts of conditions and objects are receding way off in the distance and getting hidden by the bulge of the earth. I mean, I've got very nice photographs that show that.
Yeah, you see
In other words, it's really hard to do a Cavendish experiment in a hurricane.
Exactly.
No, I understand that. If you look at the video, the actual conditions are pretty calm, but I understand obviously that refraction can obviously happen the most in calm conditions like that.
Yeah, I found the very best conditions to be making these observations. You really don't want still dead air. That's the worst. You don't want to be within an hour of sunrise or sunset. You want to kind of be, I found the very best conditions tend to be around 3 hours after sunrise. And if you have a breeze, not necessarily a crossbeat breeze, but one that's kind of going down your optical corridor at an angle. Like I'm shooting east-west, and if I'm getting a breeze, about a 5-10 mile an hour wind,
I get that.
that's coming out of the northwest, that's mixing the air good, I tend to have my very best optic viewing conditions.
Because Jose's wasn't that bad. He did have heat haze on there, and you could see the heat haze, but it wasn't like bobbing up and down, compressing or anything. It probably did have compression on it, but it wasn't like one of those bobby up and down, squashy sort of like thing. And that, again, he was at 17 feet, which isn't too much for 23 miles, obviously, but you would have thought you would have got over at least a lot of that refraction layer that you're saying is the cause of it sinking in.
Well, one of the things I'm doing now, that before I start making my measurements, I will look over to Franzen Island at 2.72 miles away that has this beautiful channel marker structure, and I will make a few measurements on there, horizontally and vertically, and I know the distance precisely within centimeters. And by using the angular measurements between, say, points on that structure and using the distance calculation, I can compute, say, the width between points on that structure, and I know exactly physically what those are because I've gone over there and I've measured them with a steel tape rule. So then I compare what I calculate to what I know it should actually be, and if they don't agree within, a reasonable amount of error bounds, I'm not going to bother making my measurements because I know there's refraction occurring at that point in time because the two numbers aren't agreeing. So, why try to make my observations at that point? No,
I get that. And I do commend you on doing that because that is a lot more in depth than anyone else is doing. But again, on that to record that rather than to ditch the day, let's say, to do just a one recording, let's say, would be good to understand the variety the differential between that.
Well, yeah, that's part of my investigation. But I'm saying, as far as taking photographs to demonstrate what's being hidden or not hidden, I won't do it when I know there's a significant amount of refraction. I'll just spend the day now accumulating data and trying to understand the refraction more, get to see if I have compression, expansion, and then make the temperature measurements so that maybe we can use the refraction equations eventually to try to put some theoretical calculations, given the temperature and the distances and stuff, to see if it agrees with the actual measurements. That's ultimately where I'm headed with this.
No, that's good. That sounds good. That does sound good. Seriously, because that would, I reckon that you could do a very, very good approximation in knowing your control. Let's say if you knew your medium or your mean, your average of what that square would be if you just painted a massive red square 1 meter by 1 meter on a building, and then done exactly what you're saying and measured the effect of what it would have on it, then that would be good, because then that comes up with an equation rather than the 7/6R based on reality, as opposed to a mean that's taken from lots of places. Is from your observation where you are, your environment.
The difference,
salute that.
What separates what I'm doing from what people have done previously and are doing is I know precisely what I'm looking at. I know precisely the distance. I know exactly all the physical dimensions, all the points of interest on this structure. And so that allows me to make comparisons. There's no guesswork going on here.
Is this over a lake?
Yes, in fact, I'm uploading some pictures right now. I'll show you some stuff that I took today.
Yeah, no, I will keep an eye out for that, George. Normally, you know our history, but I will keep an eye out for that because you've intrigued me straight away with it.
I'll put it in the stream here and once I get my pictures unloaded.
I know Rumpus was bragging about, I can tell you this, I can tell you how much it should be. Yeah, based on a calculation of the focal length and whatnot. And there is a calculator online that does that, so it's nothing special. But exactly that is that variation on real world is something that interests me. So I will look out for that.
Guys, go ahead and continue talking.
Well, I'd really like you to look at Jose's thing though, because the black swan that everyone's going on about with the flat Earth side of things. I think Heath Carmoody done a basic one, and he said it should need to be somewhere near 11/6R in order to match what we're seeing. And I don't know enough about it to say, yeah, that's well out of reality threshold. Because obviously the comeback I've heard from Ruhif is you can have it go up to infinity and it will just go back on yourself. So I don't know where the threshold is where it says, no, wait there, 10 is actually your maximum that you're going to get for that.
On this one view graphic that Rumpus made, where he shows you all the different curves on a geometrical circle with different K values and this
I know that
effective radius value. I hate people talking about or mentioning infinite refraction. To me, that's nonsense. Because when you talk about refraction, I'm thinking refractive indexes, and you're never going to have a refractive index much more than 10 or 20 at most, let alone infinity. What they're referring to is this effective radius that you have to have of the Earth being infinite, which would basically make it a flat plane. So the terminology being used is rather problematic in my estimation. But the thing is on that particular diagram, next time you talk to Rumpus, ask him to point out, I believe he actually pointed out or labeled on that graph which of the K values have to be for the temperature gradients that I measured. I actually measured several temperature gradients and gave it to Rumpus on the extreme refractive conditions that I witnessed. I have the actual thermistor data, temperature data of the optical corridor, and he took that data and worked out the K value, and he does have it labeled, I think, in 2 spots on that particular view graph, and you might ask him about it.
Yeah, no. We'll look at that. I will look at that. If it's real data, as I say, everyone's seen his lighthouse one, and it's a bit difficult to grasp because it puts everything everywhere.
Is people have to explain to me what they mean by infinite refraction. I mean, what is a parameter? You know, how is that calculated? What does that mean? Because to me, when you talk about refraction, what comes to mind are indexes of refraction, not all these other different parameters like K values, R values, or whatever. I'd have to understand what people mean by infinite. What is the parameter? What is the metric being calculated there to give you this infinite or beyond infinite?
I would assume it's just exactly like if you imagine a plane constantly falling and getting that sweet spot of where it's neither falling in altitude, it's more falling and missing the Earth like the moon. That's how I see it.
In orbit, a light ray being in orbit, what you're essentially saying.
Yeah, just exactly that. Yeah, exactly that. Traveling perpendicular.
That's what K equals 1 does. It matches the radius.
So then that isn't infinite, though, is it? That isn't infinite then, if it's K equals 1, because it's 0.8 whatever, isn't it? And it's always down from a whole number.
Yeah. Standard days is K somewhere between, I don't know, 1.3 and 1.7 or something like that.
Oh, so it goes up.
0.13, 0.17. Goes from 0, a K of 0.
0 to 1.
Would have well, at that point you would have the apparent horizon and geometric horizon coincidence. In theory.
Okay, yeah, no.
There would be no refraction.
No refraction, which is impossible.
No refraction. And if that were true, then you would have the apparent horizon would be sitting on top of the geometric horizon.
Mm-hmm. Identical.
With K equal to 1, the curvature of the light matches the curvature of the surface. That's essentially what that means. And K can go above 1, and it can go below 0 too, and bend the other direction. Rumpus shows that in that diagram George is talking about.
Yeah. That one makes more sense than his bloody lighthouse one. It's lighthouse one where he chucks it up in the sky and it just confuses the situation. That one where he's got just the curve of the Earth and several lines, including I think the middle one's in red or something like that, and that is your 0 horizon. And then it's from there, deviation from that central point, isn't it? Going down.
Yeah.
I just loaded in the chat here for you.
I see it.
This is the channel marker that I'm looking at. And that little white diamond with the black in the center, that's a target I mounted on there yesterday. What that is 12 retro reflectors mounted on a white board. And I was using this for a laser test last night.
And that's of equal proportion. That's a square. Yeah.
Yes. Now, this structure going crosswise is 5 feet in width. And then you're not seeing at the top, but the channel marker, that orange part, has the number 12 on it. That's to give the marker designation. I have every aspect, all the members, exactly where they are with respect to the ground. And at the base, you see kind of 2 red space dots. Yep. What those are concrete blocks, 16 inches by 16 inches. They're cubes, and I painted them red.
Okay.
So that I could spot them. And I know like the distance between the tops of them and the bottom of that channel marker, every aspect of that I know. Now, the interesting thing I'm going to show you here this is looking through the theodolite. You can see the crosshairs there. And I mean, that structure looks like a pretty good view, right?
Yeah.
Everything's looked well proportioned.
The diamond, I was going to say, is actually squashed down at the top in my eyes, and it kind of drips.
Look at an expanded view now. This is the same time, just a few seconds later. Look at that. Look at how distorted that is. So there's obviously a lot of refraction going on here.
Yeah, definitely. Yeah, that is almost like if you can understand, there's a big thick bit where the bubbly bit goes just underneath the diamond.
Yeah, I mean, the member's hardly seen there, and there's so much distortion in the members. And this is what bothers me about these photographs being presented and looked at. I mean, you can fool yourself. I mean, depending upon the zoom level and what you're looking at. I mean, in the first photograph, that structure looked like you could swear that the refraction was minimal. But now when you zoom in, you see that there's all kinds of distortion going on here. It is not a very good day.
And plus, I mean, I've always said it. I've said it about the Black Swan. I've been asked about it live on Jose's, even by Ranty, and I wouldn't even bother putting my eggs all in one basket and even though he's gone back and whatnot and done, even then, it's exactly that. I don't see it as definitive proof. Maybe supporting evidence, but as any sort of, like, we're talking down in the 20-30% worth of value.
Well, look at this now.
Evidence.
Yeah, the zoom level is even higher, and look at that. The retroreflectors in the center are not well proportioned. There's more. It's not symmetric like it actually really is.
And that's what it is as well. When you're analysing just a one-shot photo as well, you're getting that condition at that time. And it's sort of like two seconds later, it's a completely different photo, or could be.
Exactly. And I've seen this in many live video that I've had, is you can always cherry pick and find a nice undistorted frame, but a fraction of a second later, the doggone thing's all wavy and looking like spaghetti.
100% agree with you on that, and it's inconclusive. I think it comes to an inconclusive. You can show stuff that looks like it's flat, and you can show stuff which clearly looks like it's a globe, and I don't think this picture thing is a good conclusive thing. However, I do value what you're doing here. What you're doing here is a real world thing, taking something known and that has an effect in between you and it, and you are recording that effect, and it's that you're measuring as well, which is good. I mean, how much distance can you get on this? What I'd really love to know, George, is how far can you go back before the theodolite turns that whole square into 1 pixel, or you lose?
I can't do that. The furthest I can view down this particular corridor is 6 miles, and that isn't enough to reduce that target to 1 pixel. Now, there's other parts of the lake where I could do that. I do have a 21-mile clear view shot on one other part of the lake, but it's a lot more effort to go and set up my equipment and that. Whereas this is really easy for me because I'm just at the end of my dock and I can leave things set up and go view throughout the day, at particular parts. I don't have to tear down and set up all the time.
Yeah, definitely. No, it wasn't to do it because it's just a personal interest of just understanding the diffraction limit of the device. And it doesn't actually matter in what you're doing here. It was just a personal, I'd like to know what that would be on a theodolite, because I've not calculated it or even attempted to try and calculate it, but I've looked up the likes of cameras and telescopes, and they're pretty easy to find out whether they are diffraction limited or what their actual limit is. But on theodolites, I've never found something that says, right, this is the limit of your resolution on this, because they do look like they're rubbish, to be honest. If I'm really honest, the theodolite actual quality of the lens do actually look rubbish. but
Oh,
it's
not on this one, not on this TopCon. I tell you, the optics on this thing are first rate, really high quality.
Well, I'm only saying that, sorry, because it's only rubbish because you're zooming in so much. That'll be on those
There's
different.
also a
Is
lot
that
of-
the same device there that you're zoomed out on, or does it not
Yeah,
even
it's
have
the
a
same
zoom?
thing. It's a theodolite, but the thing you have
Yeah.
to keep in mind is during today there was a fair amount of haze in the air. That's what's causing.
Yeah. No, I get that. Yeah. That's me prejudging. But you know what I'm saying when you can see, let's say, some of sound photos in comparison to somebody I think it was Jesse, wasn't it, who put a theodolite, or was it yourself? Put a theodolite next to it on the little grass mound next to the pylons, I think it was.
Yeah, it was Jesse.
Yeah, Jesse. Yeah. And again, it's sort of like when he zoomed in onto the horizon bit, it just looked low quality, low pixelated, sort of like not sharp and crisp as the one that you've just shown there, the zoomed out one.
Well, this last photo here is a more wide view, and what you're seeing, the trees in the background, just to the right, you see the channel marker. But those trees in the background are on what's called Home Island, and that's 6 miles away. That channel marker there on the right is 2.72 miles away,
Okay.
and the trees in the background are 6 miles away. And if you go about 2 of that channel marker to the left, you see a little white dot in the trees. That's my 6 mile marker.
Okay.
Target I have mounted in the trees. That's about 36 feet above the ice, and that target is actually about 5 feet in height. Of course, I'm not zoomed in on it right now.
Yeah, no, I can see it, and it does look kind of in proportion as well. So how far was that? The
little
diamond
white
ball?
dot is 6 miles away.
Yeah, no, that's 5 foot up. But you said on the
Target
right-hand side.
itself, the target itself is 5 feet in height.
Yeah.
Its size, the target size is 5 feet, and it's about 35, 36 feet above the ice.
Oh, okay. Sorry. Yeah, now I get you. It's additional above the ice as well. And then obviously that sign on the right-hand side is what you zoomed.
The channel marker.
Yeah. So,
Are you taking a picture through the eyepiece of the theodolite? Is that what you're doing, George?
The picture there.
Yeah.
That is just out of the camera.
Yeah. Okay.
Out. So
But,
I get
yeah,
a wider.
But your pictures through the theodolite, you're looking through the eyepiece of the taking a picture
No.
with a camera through the eyepiece of the theodolite. No.
The last picture, that's just the camera itself.
Yeah, I'm talking about the ones with the theodolite.
Well, the ones with the theodolite or the auto level, you'll always see crosshairs in the picture.
Right. Those are taken. The theodolite's not making pictures. Is what I'm asking.
yeah, no, that's what I thought. That's what I thought, Blue, that they weren't actually doing the picture. It was always somebody taking a photo through the eyepiece.
Yeah.
Mm.
Well,
And that explains.
definitely has an impact on the clarity of what you're seeing.
Yeah, no.
What George sees when he looks through his theodolite is not exactly what you're going to see.
Yeah.
With a photograph captured this way.
Yeah, no. Well done for clarifying that, because I was thinking that this was a photo from the actual theodolite then. So it had a digital capturing device within it.
Mm-hmm.
This picture that I just posted is with the camera taken. You can see the theodolite eyepiece there. This was on a different day. This was during the summer. This isn't the theodolite. This is the auto level.
Okay.
Here.
Same thing though. Yeah, I didn't know of any theodolites or auto levels that actually had a camera in them.
No,
Yeah, that's it. I don't know them at all. I don't know them at all, and that's what I thought exactly. Is that when you see all the photos done through them, they were all real grainy and real crap, and that's why I was thinking that surely the newer ones have got that, but obviously I'm completely wrong because I'm not clued up on them at all.
This is, again, looking through the theodolite zoomed in on the channel marker, and you'll see what the marker looks like.
Yeah, gotcha.
Yeah. Be damn clear. 2A
That's
is quite obvious.
Yeah, that's almost 3 miles away, and the width of the tower structure is 5 feet across.
That's about the same width as the crosshair, isn't it?
Width of the crosshairs.
Yeah, just one of the line. If you took the x-axis of the middle crosshair and moved it along to the right.
I'm talking between the left and the right members, the vertical members on the tower.
Yeah, no, I'm
Separation
the same.
is 5 feet.
Yeah. So it's the width of the actual tower is 5 feet. Forget the sign. The width of the actual tower, which is about the same width as the crosshair. Channel Q is trying to. I think Channel Q's becoming a flat earther because she's putting a flying spaghetti monster in all of your photos there. She's not talking though.
Looks like spaghetti, George.
Say what, Q?
Your pictures look like spaghetti.
Oh. Little sauce on it.
Yeah,
Well, I guess
ones
you
with
did.
Meatballs.
Meatballs, yeah. Of that little white dot in the distance, that 6 mile target I was telling you about, Gleem, here's what it looks like through the theodolite. You can see it. I've got it bordered there between the two crosshairs.
Yeah, no, I get that.
Way.
It looks odd though. It looks as if it's been pinched either side, isn't it? On the.
Not sure what you mean.
Sort of like this
target
near the middle.
Target is not square. The target is rectangular, where it's longer in the vertical dimension than in the horizontal.
Okay, that makes sense. Because on the left-hand side, you can see it longer. Yeah, no, that's cool, and exactly that. I will keep an eye out for that because that intrigues me on what effect does the atmosphere or refraction have on its angular size, because you can make measurements to the cows come home, and exactly that. It can be different every single day. You can get a building, let's say Travis does it, plain truth. And he's got a building which he can show that the bottom bit does get refracted a little bit and it stretches out. And I've measured the pixels on it, and it can be up to sort of like 50 pixels if he zoomed right in. And then it's taken up most of the photo. So to know real world effects, I'll keep an eye out for it, George. Good. I like it. Better than your average nonsense of just looking at a photo and going, yeah, I'm going to put a ruler on it.
Oh, this was just done the other week, and you'll find this interesting. This is looking out at the channel marker, but look at the miraging at the bottom there. As you see a mirror image occurring. But when you get up high enough, you're out of the refraction zone. You don't have going on.
See, that would be interesting. That would be interesting to. Have you got a drone, George?
No.
No. It's to exactly that. So what you just said there is that you got up higher and you reduced that mirroring zone. Was it to 0?
I don't know.
You could see everything clear, or was there still that mirage there? But yeah, that's it. You reduced it considerably with an angle, or with height, because you're getting over that refractive zone.
Oh, here's 2 photographs, one taken in the winter, one taken in the summer, from the same point in the lake.
Okay, the bottom 2, yeah, side and side.
And
yeah, okay.
you can see how things have loomed up. If you wanted to compare side by side, on the left on the channel marker,
it's the marker.
rock.
The marker is the key thing there. Yeah, that
Right.
looks like it's gone right up, at least the size of the sign. Am I right there? Is that?
No, you're correct.
Yeah, yeah, I'm seeing that. No, that's it. And I've seen so many people deny that this happens. Denies that the actual whole scene moves. It's more, yeah, no, you'll get some refractive effects, which will make everything move at the same time. But this, clearly, you're showing that the trees are not moving at the same rate as that marker.
The trees are at the same height.
Yeah, yeah. They look identical.
Yet the stuff near the base of the marker have definitely shifted.
Yeah, yeah, that's it. It's as if the trees in the background are still the same. It's just there's more thicker atmosphere that you're looking through. But yet,
Here's the same photograph where I drew a bunch of lines.
yeah, I get you. Yeah, see that? Isn't it interesting on the just below the marker, the land below the marker? Where, I mean, why would that be white? That isn't going to be, is that the bushes? Or just reflection? Is that just reflection of the sky or something?
Or the ice,
Right, yeah. So you've got ice there on the bottom of the land. So that would normally be green. Yeah, that's it. And that's what I'm saying. The top of the land is even risen up. But yeah,
And there is no distortion.
Yeah,
There's
that's
a
it.
lot of distortion near the horizon line.
Yeah, yeah. Because then if you look at the top, if you follow the tree line, forget the very background ones. It's the ones right next to the marker. And I assume that they're going to be at different distances, aren't they, to the marker? But they look in line with them.
Well, the trees that you're seeing to the right of the marker are on the island that the marker's on.
Okay, so they are.
They're a
in line
little
with it.
bit in the foreground from the marker, maybe by about 30 feet or so. So not that much.
Yeah, see, I'm not noticing as much of a major difference in the trees as I am with the marker. The marker looks like it's gone woof, at least, as I say, a fifth up, a fifth of the total size of the marker up, whereas the trees are all staying at the same similar sort of like altitude. So it's exactly that. It's the compression increases as your elevation decreases. And is that then compression upwards? That would be, wouldn't it?
Oh, I wouldn't say it's well, yeah, there's a little bit of compression. You can see between the bottom of the triangular side and the rocks on the left image, that tower is compressed a bit.
Yeah, and even on the far right, where the land again has come up.
Yeah.
So it's as if the land has come up at the bottom, but the trees have not compensated and gone up with it, and they've just stayed the same. So it is just a...
Yeah, I mean, it goes to adding, validity to the thing that once you get up out of the humidity zone layer above the lake or the ice, you encounter less and less refraction.
Yeah, I'd like to see the up. Have you got the up one where you're minimizing that mirror band? Because the one on the right there looks like that is no mirror band at all.
That's a pretty low refraction day, I would say.
So they're both at the same altitude, though?
Oh, yes. Yeah, same spot of the lake, same altitude.
Now, that's interesting. Interesting to note that there's multiple things happening. As in, some things are staying still, staying put, and some things aren't. Some things are moving. And that's interesting because that affects proportionality. in between the distances. So if I was to say, right, I've measured a tree in the background there now, and then I try and proportion or apportion the angular size of the sign, the channel marker in the left one, then you can mess up all your angular size calculations just by that. And I guess that's why you're doing it. That's why you and Rumpus have banged your heads together on that, to say, look, we're gonna
I'm trying to do something where we don't have to introduce a lot of guesswork, you know.
Well, put it this way: that accounts towards accounting for perspective, and that's the thing. A lot of people get me wrong on that, and I'll still fight for it, to say that perspective has never been accounted for in a comparative test. Just your basic angular size and stuff like that was just ever calculated, you know, back in the days, 2-3 years back. And it is interesting. It's interesting what you're doing there, George. That's one thing definitely that you prick my ears up about. And that photo alone shows there's
something that's been done. I did a few winters ago. This is where I was doing my target test, where I set up 2 sets of targets.
Okay.
Upper and lower targets. And what you're looking at here is the target on the right. That's at 1.36 miles. Now, keep in mind that I proportion the target sizes for perspective, that the targets in the foreground are much smaller than the targets in the background. For example, this target in the foreground, on the 2x4, the brown 2x4 there, this target is about 15 inches or so in height, okay?
Okay, yep.
Now you have the orange target next to it, and then right behind that orange target is my 6-mile target.
Okay.
The height of that target, rather than being about 15 inches high, is actually about 63 inches high.
Okay, yeah.
Huge target.
I get what you've done. You've tried to put it on a horizon, but
what I tried to do is make it so that when I view the targets, they all look at about the same size.
Yeah. So, in a sense, mathematically, these should all be in line. But what you're saying is the further we're going back,
them off to the side, so the ones in the foreground wouldn't be hiding the ones in the background.
Yeah. So they're not all just on one line.
And actually, over that 6 miles, I had to spend a lot of time precisely placing
that angle.
Targets. These targets are displaced no more than about 3 feet off a center line.
Yeah, no, definitely. I get that. And over 6 miles, that's decent. That's decent to even get it anywhere near. You be lucky if you didn't have to go back out there.
The way this goes is the one on the right is at 1.36 miles. The orange target is at 4 miles. The next target is at 6 miles, and the leftmost target is at 2.72 miles.
Okay. And are they all in water? Because that's reflections at the bottom, isn't it?
Oh, they're on ice, mounted on ice.
Okay, actually drilled into it. Good. Yeah, that's
good. It's the only way you could. You can't do it in the summertime because the lake is much too deep to try to plant any poles. I mean, in that part of the lake, it's 50 feet deep.
Gotcha.
But in the wintertime, it's very easy. You just drill some holes in the ice, mount the poles, and freeze them in place.
That's cool. And then what was this to show, though?
Oh, well, what this is on over an average of 70-some days, I went back and forth and tried to line the targets up so that they're all lined up with a tangent that is on the upper targets here. And here we have a little bit of refraction going on because we see the furthest target being loomed upward, and the one at 2.72 miles, the leftmost one, is loomed up a little bit. They were on a low refraction day lined up so that their centers all lined up with the horizontal crosshair. Okay.
That's it.
Now, once that is done, then what I did is I went and drilled a hole beneath the base of the targets to let the water level come up and measured the actual physical distance between the center of the target and the surface of the water. Okay.
Right, okay.
So if the earth is flat, those distances should all be the same.
Mm-hmm. Getcha. Yep. I getcha.
As with the distances that I measured, it fit rather closely to the 8 inches per mile squared, because the target there at 6 miles, the third target, the one kind of in the center there, loomed upward. That's actually 30 some feet above the surface of the water, 36 feet above the water, whereas this target in the foreground was only about 15 feet above the water.
Yeah, I get you. And then even including the angular size change, you've accounted for curvature as well.
Right.
Yeah. So the curvature over, and this is solid ice all the way through. So from the 2 mile to the 6 mile, this is the whole lake basically. No land.
Right.
Yeah.
Right.
No, I get that. Get that. That's interesting. Interesting, as Jeranism would say. That's it. But yeah, you again, that's another measured effect at distance as well. You've got an incremental distance going there, so you understand how much each stage, each marker is looming up. And sorry, that red one though, that red one is before the far one on the left. Is that correct?
Oh, the red one's at 4 miles.
Okay, so the one on the left was 2 point something, wasn't it?
272, about 3 miles.
Yeah. So yeah, I mean, would the center of that be the center of it, meaning that it looks like it's going down?
Center of what?
Yeah, if you would have lined them up, let's say there was no refraction, those egg timers, let's say the line would be directly in between them all, but where would it be on the orange one? Because in the reflection, it looks like it's
center
two.
where it is.
Yeah, is it a so sorry, yeah, that is the dead center of, let's say, the oblong that
That's
you've
right.
got there. Yeah.
Yes.
Okay, so I get you now. So
You
that
can
still
see-
hasn't loomed. Yeah, that still hasn't loomed up. Put it this way, I would expect it to incrementally loom up more.
You would
more.
with the uniform gradient with distance, but you're not guaranteed that that's happening.
Yeah, no, I appreciate that.
If you notice near the bottom on the orange target, there's a lower set of orange targets. That's at 73 inches. And then to the left of that, there's also another bottom target. I have lower targets that were all set exactly 73 inches above the water level.
Gotcha.
That was kind of like a Bedford level.
I was going to say that's your Bedford thing, and watching it go down. Yep, that's it. And then you could obviously go above that, or X amount of meters that you've put as assuming a flat Earth, let's say, and they would all be in line. And then you're skipping over that refractive zone that would bend those dots down.
Right. Yeah.
Yeah. No, I get that.
Those are the lower targets. Looking at the lower targets at the optics of the auto level, which is those crosshairs there, are at 73 inches above the water level, as with all the lower targets. And you notice that as the targets recede away, they appear to get lower and lower.
Yep. When they should be staying at the same altitude. Is that
if it
right?
were flat. Yeah.
Yeah. Get that.
And the distances are the rightmost with the bluish green pole, that's at 0.7 miles.
Mm-hmm.
The one next to it to the left is at 1.36 miles. Then when we go to the leftmost target, that's at 2 miles. Then the one to the right of it, where there's 2 targets, an upper and lower, that's at 2.72 miles. The one just to the right of it is at 3 miles. and then the orange lower target there is at 4 miles.
And that matches up.
Yeah.
With
Yeah, if you count pixels and stuff, it
yeah.
You go, my gosh, you know, it following the 8 inches per mile squared.
Mm-hmm. And that's sorry, just on basic standard refraction, so just a fraction off of that. Yeah, no, interesting.
The thing is if the Earth were truly flat, the centers of all these lower targets should line up.
Yeah, no, I fully get that. I fully get why you've done that, and I fully get why you've done the dots on the bottom for the Bedford to say, yeah, no, it's bending down. And then you've obviously got the targets at the top. Yeah, no, that's especially over ice as well, which from a flat earther point of view, if it's frozen ice, it's still going to be flat.
Well, you have to remember that I did not make my measurements relative to the ice. I've made all my measurements, set all the targets to the water level. I popped a hole in the ice and let the water come up, and then I set the targets 73 inches above the surface of the water, not the ice.
Yeah, you see, and I will say that is the downfall of the one that I showed you the other day with the lights. You remember the lights one? He done the similar thing, drilled into the thingy and put cones out with lights on. Yeah, but he didn't go above that. It was all on the horizon.
When I watched that video, I'm very suspect that ice isn't hung up on the riverbed, because when they drilled, they just used a little drill, and I didn't see any water come up. I saw maybe some slush, which is telling me that the ice is resting on the riverbed.
Yeah, no, I get you there. It didn't actually pour up, did it? It didn't pour out like gold.
It would pour up. If there was significant water under the ice, it would be shooting up initially.
No, I get that, because it's pressure release, isn't it? So it'd suck it up anyway, and it would just create a pool.
Well, what happens is once you pop through the ice, is the water rushes up and it overshoots and comes up over the ice, and then it settles down. It pumps up and down and then finally settles to the right level.
Yeah, gotcha. Yeah. No, interesting. I would look out for him, George. You got my attention, mate. You got my attention with that doing the angular size thing.
It's not going to happen real fast, Gleem. I mean, this stuff takes a lot of time, a lot of setup time, a lot of measurement time. And you don't always have the right conditions every day. Like the other day, I had to abort because it was snowing and blowing like crazy out. Couldn't see a thing.
No, I'm glad to see it. That's because, put it this way, George. If you then come back and account for perspective, account for this, and say, look, I've made my calcs for this, and it includes perspective, then salute to you. Because I don't know, the only thing I cluck for is exactly that. If you're going to compare the two, or if you're going to beat the flat Earth, you've got to beat them on their terms. You can't keep on saying no. Perspective's got nothing to do with it. No. Refraction's got nothing to do with it and stuff like that, which I know you personally haven't said, but there are many people out there saying.
This is showing you. Okay, go ahead.
Yeah, no. It was exactly that.
I'm just going to show you the design of my targets. What? This is the 3 mile target.
Okay,
and the reason why I designed them this way is that you can tell how you're aligned to the center with the crosshairs, is by having the points of the triangles pointed to one another. If, say, you're off center, you see more black, above than below the crosshair, and you can easily get yourself lined up to the center this way.
Yeah, I call them when I do topo. When I used to do topo with my dad, and I used to be the reflector guy. We used to call those the finder targets. It makes it life 1,000 times easier than trying to find a circle.
Yeah, definitely. No, I get that, because it would be pinpoint exactly that. When you've gone too far up, because you'll see more at the top than the bottom. Right. Anyway, it's coming up to 1 o'clock in the morning. I'm going to get off. Salute to everyone. George, I will keep my eye out for that. You prick my ears up with that exact angular size thing, because I'd like to know the results as well. So, and again, I know that you're not going to rush anything, but I'll keep an eye out for that, because Rumpus mentioned it the other day, and I thought, no, what the bloody hell is he up to now? And he had mentioned, no, I can tell you the angular size of this. And I was like, well, wait there. There's refraction effects going on there. And exactly that. You've already obviously got on it. So salute to you for that. And I bid you farewell and good night.
Yeah, thank you, Gleem. I appreciate that.
Maybe you can appreciate the effort that's going into this.
Yeah, no, definitely. This is not a 5-minute thing. You can see that 100%. Definitely.
Yeah.
Salute to you, George, for that. Definitely. I'm intrigued. There we go. That's the word for it.
Right.
Well, I wanted to say thank you guys.
Well, I'm trying to be as unbiased as possible and just collecting data and making the best possible data set that I can, and then I'll let all you others argue over what it means.
Yeah, exactly that.
Well, thank you guys. I wanted to go ahead and end the stream. George, definitely thank you to you today for everything that you've explained and helped us out with. I definitely appreciate that. And especially, overseeing what many thought happened earlier, overseeing that and realizing that I was just trying to understand it. So I do appreciate that myself. Thank you very much.
Oh, is Gleem still? Yeah, Gleem.
Yeah,
one of the issues that you're dealt with on this is I'm going to show you. This is my 4-mile target. Now you can appreciate when you look at the Bedford level view. Look at that orange target, how low to the ice it is there.
Sure.
And then the one at the top where it's at 36
so you can
minutes
see
there. You can see how tall this mountain is. I mean, the logistics, I had to tether it. I had to drive stakes into the ice and tether it with guy lines to keep the wind from blowing the damn thing apart on me. Because that pole there, that's a 4-inch sewer pipe, that brown or green blue pipe, that's 10 foot high, and then I have a 24-foot 2x4 strapped to it, in which I've mounted the top target. Now, I was fortunate that at 6 miles I had Home Island and I had a rock hill with a tree on it in which I could mount the 6-mile target, get up to 36 feet. You try to do this out on the ice and it's virtually impossible. How are you going to build a structure that's going to be 36 feet high, that's going to withstand the gale winds out on the ice and that, Yeah,
you need one of them baskets with a snake in.
Yeah. So about 6 miles is the practical limit for doing this sort of thing. See, if you try to go out, say, to 10 miles, you're going to have a structure, 100 times 2/3, 66 feet high.
Yeah, that's it. That's surveying, and that's the crossover.
Logistically difficult to construct,
Yeah, no, that's it. That's exactly when the threshold is for plane surveying, isn't it? At the 66 foot. Because that is getting into a bit of error deviation ground.
Yeah. So I'm rather blessed with the fact that I have this good optical corridor that goes out 6 miles to this home island in Canada where I can mount things up on the hills and in the trees and stuff and not be saddled with trying to figure out how am I going to build a mounting structure to stand out on the ice to mount these things,
Yeah. No, I get you. Like
a target at 5 miles, because this is why I don't have a target at 5 miles, because I just couldn't build a structure at 5 miles to be in line with all the other targets, No,
I get that. And that is, to be honest, that is logical. In my mind, what you're doing there with the 2 targets is logical. Is, put it this way, it's a lot more logical than what bloody Sly Sparkane was bloody attempting. Of just that.
Well, no comment on that.
Anyway, I'm going to go. Thank you very much for your time there, sir. And I will catch up with you shortly, no doubt. Take care. Have a good one, Sean. Oneness.
Have a good one, Will.
Thing that you have to, oh, the other thing I was going to mention here, Gleem, is what I had to add is you have to remember back on my observation, I'm 13 feet, so I have to start at 13 feet and then add for the curvature of the Earth. So say at 4 miles, you know, we're at 16 times 2/3. So I've got to add 10 feet to the 13 feet. So I have to be up about 23, 24 feet, which is the upper target, you know.
Yeah, yeah.
So that's what makes it added difficulty. Seeing at 5 miles, I would have to be 17 feet plus 13. So I'd have to be 30 feet up, and that was just getting impossible logistically to handle.
You know what would get around that? And this is not a silly suggestion. I don't mean this silly, although I'll probably say it, and your initial thought will say, "Nah, that's stupid."
Getting it from my what the hell are those drones?
No. More is it will sound stupid if I say fireworks, because if you can get a timed device that you know the delay, then you can
but the problem with that logistically is, you know, getting everything timed and finding the right day and all that, and then you want something that's permanently going to be hanging there, so you can compare it throughout the day. You know, I look at these things during the morning, early afternoon, and late afternoon.
That's it. If they're permanent,
you want something that's going to be stable, that you can compare against day after day, week after week. You know,
that's it. A gust of wind could take them fireworks in it for them.
Yeah. But if anyone can come up with an easy way to, you know, build structures, I mean, there's a lot of work that goes into planting these things, and I would like to do something on the longer corridor in the other part of the lake, but I just can't think of how to go beyond 6 miles in a practical sense, and building structures out on the ice to get the targets to line up, you know.
Get that. And have you got a side view of the whole thing, though? Could you go from a side view and see?
No, not really.
No, that's cool. Either way, I'm going to have to go now anyway. Salute to you, and take care. And I shall catch up with you soon, no doubt. Take care. Peace.
Have a good one.
Bye. Enjoy. Bye.
All right, George, I'm going to go ahead and get out of here. Again, I appreciate it.
Okay.
And I will talk to you soon, my friend. Thank you. All right, people. Thank you for joining me. It was fun. Oh, yeah, I think Montreal was about to say something. I just saw you light up, Montreal. Are you trying to say something? Oh, okay. Okay, cool. Well, no one was talking, and their conversation was ending. So, I mean, I'll keep talking. It's just I didn't have much to say in that conversation. I was just listening.
I have a question. I came in late.
Oh, yeah, you guys can keep going. I just didn't think anyone was here to talk and all that stuff.
The one at the bottom there with the red marker, is that, are you at a 4 mile distance to the marker, or is the background 4 miles?
I'm pretty sure he was it's the distance between him and the marker.
Yeah, that's 4 miles between the observation post and the marker.
Yeah.
The background is another 2 miles away.
Okay, so I was thinking, don't get upset, George, that I'm not trying to knock you. You put in a lot of work here. I respect the big work you did here. I give you props for that. But I have, if you're 4 miles behind that red marker, right? What was your height?
13 feet.
13 feet. So if I heard you correctly, 8 miles per squared, what you were saying before, that you agreed with that. Isn't the horizon too far away?
You cut off on me. Is the horizon what?
Too far away. He said, "Is the horizon too far away?"
I'm not sure what you mean. You mean in any of these photographs? I mean, this bottom photograph that you're viewing is not from my observation point. I'm only about 20 feet from the target when I took that picture. Just that's to show the targets, what the targets look like.
Yeah, the
Okay,
picture that
so there was a misunderstanding.
Yeah, what George was seeing through his instrument would be more like the top picture on that last post he did of the three. That's what he would have seen through his.
The two bottom pictures are just part of my archive showing the targets mounted. I was only about 20 feet away from the targets on the two bottom pictures. Is just to get a picture of them to document the markers and how they were mounted.
Okay, I misunderstood. Anyways, I'm gonna go back and check your stuff because it's very interesting, and I gotta give you props, George. You put in a lot of work, so I'm gonna check.
Hey, George, do you have a lot of people that like use your uploads or the footage like this that you have that actually, and they try to argue against it, or do they just leave it alone?
No one ever, no one ever has.
There's a good reason for that. Very good reason for that. You know, this is one of those things where I don't care what you say, you're not going to argue against it. Not only is he seeing what we believe, or predict, assume, whatever you want to say, it's correct. So, yeah, I could see how they couldn't put holes in this at all.
If you look at the two bottom photographs, the second one from the bottom and the third one from the bottom. For example, here at the third one from the bottom, where I have the little lines looking at the Bedford level type lower target.
Mm-hmm.
Okay. On the one showing all the targets there, the third one from the bottom, if you count from the left, 1, 2, 3 markers, the one that's between the orange and the double target pole, you see that single one on the sewer pipe there?
Yep.
That's the close-up right below it. That's
okay. That's
that's
that one. Okay, I see.
Yeah, that's that target.
Let me ask you, George, if I may, how did you eliminate perspective from that picture? Because it looks to me like lampposts going down.
What I did is I scaled each of the targets according to distance so that when I looked at them from my observation point, they would all appear to be the same size.
So as you got further away, your targets got bigger.
Exactly. Like the target on the third photograph from the bottom where we're seeing all the targets, the target on the right side there, that horizontal target
on the pipe,
that's only 8 inches in width in the vertical direction. That's 8 inches. Okay. Whereas the target just to the left of the vertical crosshair, that's way in the distance there, that's actually 63 inches high. You know, they've been scaled so that they appear all to be about the same size when I'm looking at them from my observation point.
So you mean the posts are not all the same height?
Well, they aren't. No.
Okay.
But
the sewer pipes themselves.
George, you did that I'm sorry. You did that for your convenience, or you did that for what convenience? The size of the targets, because when I do topo,
I wanted to be able to see the centers and compare them. As I go out to easily align them when I was aligning them with the auto level. Because if I had made the targets all the same size, by the time I got out to 6 miles, I'd never be able to center it.
Yeah. Well, I just know because like when me and my pops used to do topos, our distance, well, you know how the reflectors are, you know, they're 4 inch, 6 inch, and 8 inch. So you would use that, but I could see you not wanting to do that because you're by yourself too. You don't have
Right.
the luxury of
was
finding it
extremely-
easier.
It took me 2 weeks to get all the targets set.
Oh,
you
you
know,
had to do
whereas,
center line and all that.
think about it. To get the target set out at 6 miles, I had to travel out 6 miles, adjust it, go back 6 miles, look
Check
through
it.
say, oh shit, now I gotta, make an estimate to how much to move it up and down, go back 6 miles, adjust it, come back,
Oh,
look.
George, get to GPS.
Gotta do
Stop
these-
that shit. Get yourself a GPS system, and then so you don't have to do that no more.
Oh.
No, I'm just kidding with you. You know that. I'm just messing with you.
Yeah. Whereas if
It's-
I had a helper and we were
Yeah.
talking via phone or something, I could say up a little bit, no,
Yeah.
down a little bit, there, done,
Yeah,
and
exactly.
that shot would be done in minutes, whereas this took me days, weeks
Yeah.
to do.
I know exactly what it went through. 'Cause I could only imagine having to do topos by myself.
Answer
now they have GPS, but
to
that's
answer
But-
to answer Montreal.
Mhm.
The mounting poles are not all the same heights, but the ones that are the blue-green pipes. They're 10-foot sewer pipes. So the one on the right, you can see the sewer pipe. The one on the very left is the sewer pipe, and then the third one from the
In the
left
back,
is the
yeah.
sewer pipe. So you could essentially say the tops of these sewer pipes are all 10 foot above the ice, roughly.
What'd you have? You just had a couple 20-footers?
Oh no,
Right.
I used the 10-footer as the base pipe, and then if I needed to go higher, I would strap a 2x4 to it.
Oh, okay, yeah.
It's actually the second target from the left is also got a green sewer pipe, but the 2x4 is strapped in front of it, so you can't really make out the sewer pipe. But the first 10 feet, the 2x4 is strapped to that sewer pipe to anchor it, and then I use 24-foot 2x4s strapped to the sewer pipes to give me more height.
Okay, yeah.
Give you I'll find a photograph here of one that you can easily see. Let's see.
Yeah, because you just mounted. Because that the horizontal orange ones, it almost looked like a reflector pole at first, and then I realized that it's wood.
Yeah. Well, hang on here. Let's get you one that you can easily see.
Those are comments.
Here's one. This is the 2.72 mile target. And you can see the 2x4 strapped to the sewer pipe there.
Okay, yeah.
When you say 2.4 mile, you mean you're at 2.4 miles away from this target, or the background?
No, I'm only 20 feet away or so taking this picture. When I say this is the 2.72 mile target, this is the mounting pole is 2.72 miles away from the observation station.
Okay. Well, I gotta give you props, George. You're putting your money where your mouth is. You're doing the work, so respect for that. It's very interesting, this. What I don't understand, George, why aren't you using the top of the poles? What's the significance with those boards you?
Easier to align to the crosshairs. You can't always easily make out the top of the poles out in the distance.
Yeah, at 4 miles, that 2x4 looks like a piece of floss almost.
Okay,
that's
I
what
get
it is. That's really what it is. That's why those targets are designed like that. Because even when you use the normal size reflectors that go on a pole for surveying, they're designed that same way. They have little reflected little triangles that point to each other, so it just gives you a better find for it. And that's what instead of trying to look for the pole only. But that's an excellent idea, especially when you make them so large for the distance. Yeah, I can see how that distance normal reflectors are pointless.
Yeah, well, good luck seeing that friggin' pole from 6 miles away.
Exactly. That pole's almost not
George, a final question, if I may. Are you saying that with this experiment that you did, are you agreeing with the 8 inches per mile squared formula? Is this what you're getting at?
Yeah, the upper set of targets give you that information. Yep.
Interesting. Very interesting. Good stuff.
Is when you measure the center of the target to the surface of the lake water when it comes up in a hole drilled through the ice, and you measure all those distances from the centers of the upper targets to the surface of the water, and then subtract off the observation height, it agrees very closely with the 8 inches per mile squared.
I'm still processing the information, but so far it makes sense to me.
You must be in La La Land.
Hey, I always say the truth, Blue. If I see it, if it makes no sense to me, I'll say it. If it makes sense to me, I'll say it.
Yeah, that's the only way. You have to at least ask. What were you saying, Q?
George, people like your stuff. I made you some memes to commemorate it. Those are comments directly from chat.
Oh yeah, a lot of people enjoy it when people are actually ready to explain it. It's not. George is very long-winded, but me and George had that conversation. It was like, well, if you really want to understand what we're talking about, yeah, he's going to have to be long-winded because to just explain something isn't a one-sentence thing. It almost never is, and I think once you get, for instance, George on a platform where he has the floor, people don't look at it as being long-winded. They actually go, okay, well, we're here to listen to George. George is going to give the explanation, and it becomes very clear why George, quote unquote, is considered long-winded, because he's trying to explain shit that people sometimes don't give a fuck, and then he gets frustrated. I get it. We had that conversation, so I know exactly where he's coming from.
This Montreal is my observation point. That's where the red arrow is pointing. I'm up on a rock outcropping, up on a hill, up off the ice, and you see that yellow tripod back in the woods there. That was my official observation point.
I am so jealous of your setup.
And then in the foreground, you see the auto level set up where it's 73 inches above the ice for making the measurement for the Bedford level test. And the theodolite is in the middle there.
Kudos, George. I gotta hand it to you. You're doing it right, bro.
Oh, thank you. I
sure
guess
that
I should, coming from you, I can't say that that's anything lighthearted. That I guess I should be overwhelmed that got a compliment from you.
Look, we've had our differences, George, but I think Sean is on to what the problem is. It's that you have, and I'll admit, you have much more knowledge than me, especially on this topic. The thing is that you have maybe a problem explaining it. Like today, what you did with the mesh thing, with the car thing, that was clear, precise, and again, I'll give you kudos for it.
Yeah, I've seen when me and George talked about it. I think he's not only is he acknowledged that I've seen him starting to simplify things a lot more. So I think it's one of those things where he's working on it, right, George? You could say that, trying to
It's
get
an
to that.
evolutionary process. I mean, this has been good for me over the years, is learning how to better explain to people that don't have the technical background that I do. 'Cause you have to understand, most of my career, I'm dealing with other engineers and other technical people, and we're talking, our jargon, and, it hasn't always been easy for me to try to explain things not using the jargon that I'm used to.
Yeah, exactly. Luckily, I there's a lot of topics I can catch you. I understand, like, especially every time you're talking about these control points and surveying and all that stuff. I definitely can't get it, but then I also got to remember there are people that don't. And that's kind of why I started explaining, like the reflector, the targets, and all that kind of stuff. Because a lot of people just see a big square with triangles, and they're like, "What is that for?" So it is kind of odd because you almost get complacent when you do understand things.
Here's another good photograph of the Bedford level, looking through the, in this case, looking through the theodolite.
Nice. Yeah,
you can tell that's some serious expensive stuff there.
I could see that. That's some definite curvature there. Right off the bat.
I have an idea, George.
Mm-hmm.
To simplify things for you. No, for us, actually. Like today, for example, you gave a good example of the copper box.
Okay.
When you said to get
we were
all
talking
the
about
RF
earlier.
frequencies, four quarter-inch copper box. Now, you should have started with that. You started with formulas and this and that and the wavelengths, and you should have started. The solution is the copper box, and let me explain you why. You know what I'm saying?
Okay, gotcha. Ed, it's a learning process for me too. Montreal is how to best approach things. Again, I admit I don't always take the simplest approach, but I'm learning, and I think I've improved a lot, and there's still room for improvement.
I'm glad to hear that. Like, if you talk with Blue, for example, he'll get you right away. But somebody like me or like 95% of the people that are not in your field won't get it right away. They'll say, "Oh, this guy, what the hell is he saying?"
I understand. And it's always best for you to tell me, if I'm not being clear, because then I will try a different approach.
Fair enough.
Yeah, I think my bad. Go ahead, Blue. Go ahead.
Such a diversity of people that climb into these things, and it confuses me because I understand that people are not going to, for the most part, aren't going to latch on to the technical jargon if you get too deep into it. In the very instant you try to make it simple, there's some wise ass out there that actually knows something and just knows just enough to be dangerous, and then you're kind of caught. So
yeah,
I can appreciate what George is doing, believe me, and I think I'm heading more his direction as he's trying to head more my direction.
Yeah, a little bit of there here,
Now,
both on both sides. Yeah, you got to figure out which one you're trying to balance it.
Oh, Blue, you have a good
just
approach.
To give you an appreciation.
Sorry,
give
George,
you appreciation on the target size differences. I just posted 2 pictures. The one on the bottom is the 0.7 mile target. Now remember, the diameter of these sewer pipes are 4 inches. So the vertical height of that horizontal target on the bottom is about 8 inches, top to bottom. Now the target up above it is the 6 mile target, and you can see Jesse Kozlowski there looking at it.
That thing is fucking huge.
This is standing there saying, "Holy shit! How did he put that up?"
I was just gonna ask that same question. Wow.
Holy hell! Did he get that up there?
Oh, it's huge.
Tree.
You can't accuse George of being lazy. That's for freaking sure.
Fuck no.
That's in a tree, right, George?
That is in a fucking tree. Blue, you are not seeing anything. You're not seeing an illusion.
Well,
damn.
Holy moly.
And this is a video. Jesse's just in awe of the target. He's been standing there for months.
That is a what the fuck moment.
Yeah, you guys were dedicated to this project. That's for damn sure.
And I wish I lived closer to George. I would love to go up there and help
For
out.
real. For real, I've said that a few dozen times. I'd love to fucking do a meetup with like George or Jesse, because like I'm what I call a hobbyist surveyor, because I know a lot about it. It's not enough to know everything anywhere near it, but I'd like to learn from George and Jesse. And one of the aspects of surveying is that you do have to do it, it's hands-on to learn it. That's school and shit. It's good and all, but a good surveyor, any trade like that, you're not good enough. You don't get good until you've actually got your hands-on experience, and those gentlemen have so much more than I. So there's so much I can learn.
The thing to keep in mind too, that like this set of measurements that I did was over a period of 73 days, setting all this stuff up, going out, making measurements. And to do an experiment well, and it takes a while to design a well-conducted experiment, because all you're seeing is the results. You don't see the failures. Like when I first started figuring out how I was going to mount the targets, I had this really clever scheme, I thought, and it turned out to fall flat on its face. It was a disaster. Didn't work worth a damn. And then I ended up getting these sewer pipes and strapping 2x4s to it. Sometimes you find the simplest thing works the best. You try to be a little too perfect and elegant, and it just doesn't work out in practice. And these things aren't something that you're going to set up in an afternoon, go make your measurements and go home. I mean, it takes a long time. There's a lot of logistics involved in these things to do it well.
Yeah.
It was like, what's that, like 3-inch PVC or something, George?
4-inch sewer pipe. Yeah.
Yeah.
Yeah, there's a lot when you're surveying and you're marking a point. There's a lot of check over here, check there, check over here, check there. You want to make sure you're on the right spot. It's very precise when you're using the instrument, so it's kind of like a smidge off could throw everything off, and then you got to start over. And especially if you're doing the walking back and forth to fix shit thing like you were doing, George. you want to be as precise as possible so you can move on.
Well, the way I did it is after I did an initial setting of the target, I'd go back to the observation, look at it through the auto level, and then knowing the size of the target and where the crosshairs lined on the target, then I could make a reasonable guess how much I had to move the target up or down to be in line with the crosshair.
So you were within like a 2/3 range,
and for most of them, it took me about 3 or 4 tries, because what would happen is you also had to ensure that you had fairly low refraction, and sometimes the target would rise up a little bit or lower. Yeah. When I got it lined up, I go back and go, oh shit, and it moved on me.
Yeah. Oh, that could be frustrating as hell, I bet.
It was over a period of many, many weeks that I finally was able to establish the average in which I would determine the upper targets would be, well in line with the tangent, because I had to see how they moved up and down during various conditions, and then average it out and get it set to the so-called sweet spot, where in some days it'd move up a little bit or move down a little bit, and but on average it'd be on line with the tangent.
Yeah. And that's exactly how you're going to measure the refraction that you do see. You're going to find your mean line from in that refraction throughout the days, and See, and that's the crazy part, because like remember a minute ago I asked you, how many videos are coming out from flat earthers basically that are going, this is wrong and this is why, and you said none, and this is one of the reasons why. One of the things that got me frustrated when I was a flat earther, because I knew surveying then, but I had never extended my distances to understand like how that kind of stuff works. So watching a lot of yours and Jesse's videos when it comes to surveying made me understand the holes in my surveying game, I guess you would say. But yeah, these are kind of things you can't really refute for any good reason. And I think the other day Travis and a few others were talking about this situation where the ocean, for instance, where the sea level is, and understanding, Travis doesn't understand about a mean line and stuff like that. That's kind of exactly how I would say in the beginning, right, George, how we started measuring what the refracted limits were, because we started seeing these things happen on a daily basis and whatnot. And that would be what the term of standard refraction is. It'd be the refraction you normally see on any given observation, right?
Right. Yeah.
Yeah, so and I can see
7.6 Rs. What that is a starting point if you don't have temperature data.
Mm-hmm.
It's a point that you start from, and to know exactly how much refraction you have or how much corrections you do with your surveying, you have to at a minimum measure the temperature at the observation point and measure the temperature at the target. And then there are charts. By averaging those two temperatures, you go to the charts that have been established over decades by geodetic surveyors and that, and then you go to the charts to determine how much you need to correct. But the 7.6R is something you use when you don't have the temperature data.
Okay, I see. Yeah, it's going to be your
flat Earth never have.
It's seemingly right.
They just go out. They just go out and wave around their P900, and they never take any temperature data. They have no idea what it is. They don't want it.
George, in the chat, Marty Moose is asking if you had a video of the experiment you and Jesse had done.
Oh, I have lots of videos, but I can't put them on chat here because they're typically about 20-30 gigabytes worth.
Okay, yeah, Discord ain't gonna let that
happen. I do have. You can go to my channel. I'll give you the link, and you can go to my updates. And I do have some of the video in my updates videos that I've uploaded.
Okay, yeah. If you actually type in the YouTube chat, they'll be able to go to your page from there.
Right.
Unless you want to do like the exact link, but yeah, it's another little simple way. Yeah, but to me, it's insane that and I think that's kind of one of the reasons why George isn't liked very much by the flat Earth community, because it's kind of one of those things where, again, he said it's not a today tomorrow thing, and when you really get that precise and detailed into the observations, it really shows that there is nothing to back the nuh-uhs that happen. I think it's just insanely disrespectful that people just would shrug off that much effort to the situation, because it isn't easy at all. I mean, like I said, I don't know. I know a lot about surveying. I don't know very much in the aspect of everything, but the things here that George is showing right now shows me that, one, George is very experienced in what he's doing. Two, there's no refuting what we're seeing. Three, these are some of the things that they were doing back in the day to help us have a better understanding of things like refraction today. So I mean, you can't really argue against it. There's nothing to say. If it was a flat Earth, I think Gleem and George were talking about. I'm not sure who was saying it, but it was more of like, what did you see on a flat Earth? Well, we wouldn't see what George is showing us if it was on a flat Earth. It wouldn't make sense, especially because he's doing it over a lake. And yeah, lakes aren't completely flat, but it shows us a very good observation point for distance, especially because he has a lot of distance. It shows us what the topography of the world is actually doing.
You do your
question.
All your surveying out in Southern California, Sean?
Say again. I'm sorry.
Oh, is all your surveying experience out there in Southern California?
Yeah. I don't get those opportunity for cold weather or you know what I mean.
I was going to say, man, I ought to drag you to the backwoods of Alabama and show you what surveying's like.
Oh no, I know what it's like. I may not have been there, but I know a lot of chest deep mud.
You learn the business end of a machete and a bush hook real quick.
Yeah, I've had some friends that learned out there in different areas. My dad back in the day used to tell me stories because I used to remember finding his gun, his bullets and all that stuff for work, and I used to think, why does he have bullets for work? And I found him one day, and you see all the little beads in it, and he's like, these are snake shot. I'm like, what the fuck is a snake shot? And once I started learning and I started being the reflector guy for my dad, I learned what snake shots for, because that's when my first gun was for. To have snake shots, like could do cert topo with them, walking through bush and all that kind of stuff. A lot of people don't get it, that the surveyors are like the unsung heroes of the construction world.
Surveying's a lot like flying airplanes in one respect. It's pretty much hours and hours and hours of sheer boredom, punctuated by moments of ecstasy or sheer terror, as you care to see it.
Yep. Exactly. Yeah.
The fun stuff, when it does happen, it doesn't last very long.
Yeah, exactly.
Not compared to all the time it took to get to that point.
Yep. Yeah, I remember. There's been a few times. I have so many stories of when I was waiting for my dad to get all the numbers punched into the station and wait for him to hit my point. I'd be sitting there, and a few times he'd be like, "I've been ready. I've just been watching you fucking throw rocks at little sticks and stuff." I'm like, "Oh, jeez." Yeah, you have to want to be doing it to do it. That's for sure.
Yep.
Yeah.
George, can I ask you a question? You there, George?
George stepped away.
Okay. I'll ask it in general. Maybe you, Blue. After witnessing what George just said, and once again, kudos to him. He put in the hard work. I'm just sitting here on a chair, so kudos to George. But after agreeing with the 8 inches per mile square formula, how do you guys square the circle with all the observations that we've been doing with the black swans and all these? Jose has pictures. How do you guys square the circle there?
Well, I would say, if anything, that the reason why George agreed with the 8-inch square per mile was because he was talking about his observation, and what his observation was able to see. He wasn't using it to describe the shape of the Earth. Is the best way I could say it, I guess.
Yeah, but how else would you explain that observation?
Say, what do you mean? That's exactly how I would explain the observation. The fact that he was able to see in his observation agreed with the 8-inch per square mile is 100% correct in a observation, not a measurement of the world itself.
Yeah, but that measurement is supposed to work up to 1,000 miles or something. Blue will correct.
Yeah, it works out pretty. It stays pretty accurate for quite a distance. Certainly over the distances that we talk about, it's good enough.
The 8 inches per mile square, if you measure it along the surface of the Earth, you pick up 1% error at 1,400 miles, and it goes as a square root of distance. So by the time you're out at 14 miles, the amount of error that 8 inches per mile squared gives you in drop distance from what it actually ought to be is like on the order of 100 parts per million, like 0.01%. It's negligible.
It really
Yeah,
is.
inside it, yeah.
It's simple. That's why we use it.
Yeah, it's a layman's way of explaining the observations. Very layman. If you want to get more detailed, the more precise it's going to get. And that's when you start falling away from it.
For all intent, it's you can just say it's dead on it for any kind of reasonable distance that we would normally be talking about.
Yeah, exactly.
The question was asked about video. I'm going to post the first link. Now, keep in mind, I'm not finished with my updates. I have the first video that explains the theory and what I'm trying to do. Most people will probably find it very dry and not want to watch the video, but if you're interested in the mythology and what it is I was trying to do out on the ice, the first video that I'm posting gives you that. And then go into the pinned comment, the comment that I have pinned, and it's filled with links to the updates to the video. As I progressed along setting up the experiment, I chronicled it in the videos. There's 5 updates, and in the pinned comment, it gives you links to those updates. Plus, it gives you some links to some Hangouts where I've discussed this. To Walter Bislin, did a wonderful job taking all my data and documenting it and creating animations and comparing all my observations to a flat Earth versus a curved Earth, and he modeled it. He did a wonderful job, and all these links are in the pinned comment. So if you find the video I'm posting now to be too dry and uninteresting for you, go to the links in the pinned comment, and then as an example here, I'm posting the link to update 5. Oops, that's the wrong link there. And then it'll give you a flavor for what the updates.
I'm going to share the links in the YouTube for you. So the 2 links I'm putting in the YouTube chat are the links he's sharing right now.
This is update 5 here to give you an idea. Or update 6, I guess, showing you how I ice augered to place the poles in, and made the measurements, popped a hole in the ice to let the water level come up and things like that. Kind of shows you that anyway.
I will definitely check them out, George. I'm still processing the information. I will check it out. You deserve that because of all the work you put into it, for sure.
Thank you.
Well, you asked a very specific question a while ago, though, Montreal.
You can always have it just playing in the background while you're shining your shoes or something.
Yeah, I guess, huh? Well, look, I always look at all information and I judge accordingly. So it's a lot of work put in here. I will definitely check it out and I'll make up my mind for it.
Yeah, guys, but I'm going to go ahead and get out of here. I was trying to earlier, but we ended up continuing, but I enjoyed it anyway. I do appreciate it. I'm going to say it again, George. 1,000 thanks to you. The work you do put into it is fucking insane, and everyone should be appreciative of it. I know I am, and a lot of us are that are listening right now.
Appreciate it. I'm just going to show you something real quick here. Okay. As soon as something else I'm working on. Oh, where is it? Oh yeah. Okay, here we go. Let's see. Working with lasers and been working on a collimator for my laser. And one of my lasers anyway. What the heck? Go ahead, talk while I search through the files here.
All right, no worries. Yeah, I was just gonna, while we're waiting for that link, I was gonna let everyone know I do appreciate everyone for stopping in and listening, and again, thanks to George for the information that he's helped us understand.
Laser target I just made for shooting laser across the lake.
Oh, wow.
Uses 13 corner reflectors mounted in an array.
That's badass. And that's get the return, right?
That's for getting a return on the laser light.
Wow.
I have the video show it a lot better. Let's see, maybe this one I can post. Most of the videos are fairly large file sizes. This one might. What this one has. It's utterly amazing what that damn thing
For real.
gives you in terms of returned light. Things are here. Oh, maybe not.
No worries. Well, plenty of time. But I'm gonna go ahead and get out of here. I do appreciate it, George. I'll DM you again because there's 1,000 things I want to pick your brain for. So I know we'll end up talking soon, and I'm gonna get out of here. But I do appreciate it again. Thank you.
You're welcome.
Yep. All right, guys. I'm gonna go ahead and get out of here. That was a long stream, but definitely an information-packed stream. Again. Big thanks out to George, who is actually taking the effort to realize that sometimes his explanations need to be changed a bit to help people understand what's going on. I'm definitely hoping that our friend Rumpus listened a little bit to the stream. I doubt it because he's too pig-headed. But yeah, it's one of those things to me where, again, we have a lot of people here that explain things wonderfully, or are extremely smart and can explain things, but there's also people that are smart that don't explain very well. And when this happens, what the big problem starts happening is that people aren't going to start understanding it. They're going to start hearing your points to argue against. Again, being right and wrong is different than wanting to know the truth or understanding. I would really hope that people like Rumpus hear this stream, hear how George handles situations where people don't understand and learns from it. Because if he is that smart, then he should be able to learn from his mistakes. We'll see. But with that said, I'm going to go ahead and get out of here. I will be doing a MMA stream in about an hour, 2 hours over at the MMA server. What we're going to be watching is just the John Jones Dominic Reyes fight again. Basically, I want to pick it apart and just be angry that Reyes got that title unfairly stripped from him due to terrible judging. But that's going to be fun. We just hang out. Last night we hung out. Me, Jose, and a few others hung out and just watched the fight night. And that's what the MMA channel is going to be. So if you see me at the MMA channel, most likely I'm going to be sharing a fight or something going on. So come and join us for that, have a conversation about it. I'm trying to think of anything else. I think I'll be live tomorrow. I'll be live tomorrow. Not Tuesday. Tuesday, Thursdays, and then Friday I train now, so I'm not gonna be doing that. But definitely Monday I will be, and I'm gonna try to get pick some more brains and get some more information in here, because that's realistically what I like. I like this platform for the fact that everyone and anyone can come on. And if you do need a long-winded explanation for it, as long as you're willing to accept the fact that I will have questions, you're more than welcome to come here and use this as a platform and have the floor. Again, I don't care who you are. If you have anything you want, anybody wants to present something, make sure it is as precise as you can get it, so that we are learning something and not wasting our time. But with that said, guys, I'm going to go ahead and get out of here now. I do appreciate everyone for being here again. Thank you. So with that being said, I'm out. Peace.